Hello, everyone. I'm Hongyi Li. Welcome back to the third day's lecture of MLSS 2021. It is my great pleasure to introduce today's speaker, Dr. Marco Cuturi. Dr. Marco Cuturi is a research scientist of Google Brain. He was at the Graduate School of Informatics of Kyoto University between 2010 and 2016 as an associate professor. He has joined AINTU in 2016. He still works at there part-time. Since 2018, he joined the Paris office of Google Brain as a research scientist. There's a very important information I would like to share with you about Dr. Cuturi. He was a student of MLSS 2006, which is also held at Taipei. At that time, he was a postdoc researcher at the Institute of Statistical Mathematics, Tokyo. And after 15 years, today he joined MLSS at Taipei again. It is very meaningful he can give a lecture at MLSS 2021. Today, Dr. Marco Cuturi will talk about optimal transpose. His recent proposal to solve optimal transpose using an entropic regularization has reignited interest in optimal transpose and persistent distance in the machine learning community. His work has recently focused on applying the loss function to problems involving probability distributions. For example, topic model and dictionary learning for text and images, parametric inference for generative models, regression with a persistent loss, and probabilistic embedding for words. He is the co-author of the textbook, Computational Optimal Transpose, a very important textbook for the practical use of optimal transpose. Let's welcome Dr. Marco Cuturi. Dr. Cuturi, now the stage is yours.
Thank you very much, Hongyi. Hongyi. I really appreciate your introduction, and I just wanted to first start by saying thank you to the organizers of the MLSS. As Hongyi said earlier, I really I'm part of the. I feel I am part of the MLSS family. My first MLSS as an attendant was in Taipei in 2006, and I really have wonderful memories of that time. I was lucky enough to go back to Taipei a few times after that, and in between I also organized two MLSS. So I was holding an old T-shirt of. I don't know if you received the T-shirt for your MLSS this time. This was an old MLSS 2015 T-shirt that we organized in Kyoto when I was working there. So I really think it's very important to have these events. So during these pandemic years, of course, it's more complicated, but it's important to continue. And I hope we can all reunite at some point. You know, when the COVID is gone, to have again in-person interactions. I really believe this is part of the greatest things about being in the research and academic research community. So there's the first wave of thanks goes therefore to the organizers. I was an organizer before, and so I know it's complicated and it's a lot of work for the community. And so I really want to show some gratitude there. And then I also wanted to thank all my collaborators on the topics that I will mention in the next 3 hours. And you can see a few pictures there, but of course there's many more. And the pictures basically highlight people have been working both on the ENSAE side. ENSAE is this school, a part of Institut Polytechnique Paris in Paris. And so there are several students that I've been working with, had the pleasure to collaborate with. And then on the Google side, I've had the pleasure to collaborate with fellow researchers there and also interns. So let me just dive directly into the problem, because I guess some of you may not really know what optimal transport is about. And so I will try to really start from a very concrete application-minded perspective before I dive more deeply into the math. So I will start with an example taken from biology, and one more precisely in the field called single-cell genomics. So imagine, you take a biopsy, from someone. So you just take a sample of tissue, and then you will look at that pool of cells here, and you will want to understand basically what is the driving. I mean, what is the dynamical what is happening to the cells, basically. Are they working in a steady environment, expressing the same level of genes? Or do you have cells that, for instance, kind of go crazy? And this is what happens when you have cancer, typically. And so what you would like to understand is from this sample and the way you're going to watch it over time, how one cell can basically, what is the trajectory of one single cell? So you start with time 0, and then typically in an experimental setup, you would let the population of cell evolve and keep on looking at it throughout maybe 6 hours, 12 hours, etc. Add some reactants, etc. So the great thing about the current state of the art, in terms of genomics, is that we're able to do something which was unimaginable before, which is to actually extract one cell and measure at the level of a single cell. So this is why people call this single cell genomics. A feature vector, basically gene expression levels or the transcriptome of that particular cell. And so we have a very, very fine-grained tool to basically look at a cell. And so you would hope that by looking at cells throughout time, you would be able to figure out what happens, with a cancer, a tumor, a cell in a tumor over time. Unfortunately, there's one problem, which is that you cannot measure the same cell twice. When you take one cell, you can't just put it back in the plate. Take it and measure and then put it back, because basically you're destroying it when you're taking those measurements. And so you are essentially faced with the following situation. At time 0, you have a bunch of cells. You're going to take a few of them, just a subsample, like a population, and you're going to actually really destroy them to get the measurements you need. So you're going to, this process is basically taking each cell and turning it into a very high dimensional feature vector, let's say 5,000 genes for each cell. Now, this you can do it, of course, at time 0. And then later on, you will remember that which cell was which. Later on, you have the plate, growing, the cells growing, multiply, die, etc. And then you will do this again 6 hours later. And so you will take another subset of cells, which you think is representative, again, make them go through the machine to give you the feature vectors. And then what you're actually left with is 2 populations of cells, neither of which is really, the same cell twice that has grown over time. So you cannot say, for instance, this cell became, for instance, let's say this one, because you don't have the ability to say this. But you still have, though, those 2 populations. And so if you wanted to answer who could have become who, basically, which cell could have become which cell in 6 hours later, you need to remove an ambiguity. So removing this ambiguity by saying, I figure out that maybe this cell became this one, and therefore I can more or less guess a trajectory for an individual cell. And so this is the way you would work. You would say, well, if I have to give a best guess of what cell became what cell, then maybe here the most intuitive one would be to say, okay, I would like to find a way to match each blue cell to one of the yellow cells. Of course, it could be any of those, right? It can be many of them. But since I know that I need to match one blue to one yellow, sorry, exactly, this means I need to solve what is called the matching problem. And then at that moment, when you figure out that you have a matching problem, it makes sense to take the optimal matching one. So what is the optimal matching one? So I'm not going to dive too much in the math right now. The optimal matching is essentially the permutation. Would you mind maybe cutting your mic? Because I think, thank you. I could hear some, or I can hear someone else in the background, sorry. Is there anyone else?
Let me deal with it.
Okay, so we continue then.
Yes.
So the optimal matching here would be to say, what is the best way to match one blue to one yellow? And that is basically a permutation. And so the way you would try to find the best possible permutation is by minimizing some energy of that the permutation. And this is typically what you would try to solve here. This is a really important canonical problem, which is the optimal matching problem. And you will try to minimize the sum of the distances between each of the blue points to the yellow point you match it to. And so you have here, if you have n points, of course, you would have n factorial possible matches. We know that this is a huge number, but we know that there are algorithms to help us solve this problem. So we will mention those algorithms later. So in essence, optimal transport is going to be the science of doing those matchings in a generalized way at scale and many other items that I will describe later on. But let me try to give you a feeling of why we will probably need some generalizations. So the first reason is, maybe just sorry, before I go there, I just want to mention this is at the heart of several important works in single cell genomics recently. One of them is this Cell paper that appeared in 2019. And in the toolbox that we have been developing recently, you will be able to see some examples, like a notebook that try to reproduce those examples. So what could go wrong with this very simple setup? Well, somewhat, if I just showed you, those cells that were coming, etc. This is a bit of an ideal experimental setting, because one of the things that I assumed was that you could control exactly the number of cells you're sampling from one time to the other. In real applications, it will be most likely the case that maybe at time 0 you had maybe 523 cells, and 6 hours later you have 633 cells that you were able to sample. So why would you throw away that data? So you will need to have some notion of matching that will be able to be flexible enough to accommodate maybe a different number of blue points and yellow points. So sometimes maybe you might want to say one of those blue points kind of can be traced back to several yellow points, or inversely, you could imagine that several yellow points basically explain one blue point. One of the issues that you will still have, and why this is still somewhat some matching, is that if you were to do this in a naive way, like a nearest neighbor type of rule, I'm just going to assign to a blue point the nearest yellow point, then you would fall into some pitfalls. You would have some issues. For instance, you might be tempted to say, well, because this blue point is kind of close to several yellow points, this one explains all of them. Whereas because there's no yellow point around those blue points, apart from this one, all of them collapse. So this is a bit the boundary between being mindful of trying to cover, the entire data sets of what you see, versus just doing simple nearest neighbor assignments. So this is one problem. We will need to basically deal with one-to-many or many-to-one type of assignments. The other thing that we might want to say, which is a more important goal maybe, is that here I've been drawing those arrows between points because those were the measurements that I took. But maybe a biologist, we want to do something a bit more complex, or maybe a mathematician might want to do that, which is essentially trying to not only match one point to one point when studying those data sets, but be able to infer, rather than just a point-to-point matching, infer some kind of functional relationship. So this would be like an optimal way to go from the blue to the yellows, but actually expressed as a function, like as a vector field. It would be a vector field that would have values everywhere, and I might want to that would provide more insight on basically what is going on. And you can see this type of ideas popping up very recently, even in biology. So there's this towards a mathematical theory of trajectory inference for this. Another challenge that you should envision, or people will actually come and ask you to solve for them, is what happens when you want to do matching, but this time maybe the first representation in RD was coming from a given machine that was popping out feature vectors in dimension 1000, and the other machine, you also took another batch of cells 6 hours later, but that was a different machine with a different dimensionality. And so the question is, are you still able to do some kind of matching even in that setup? Well, yes, if you go again to the theory of optimal transport. If you basically draw inspiration from recent tools in that theory, then you will be able to use something called Gromov-Wasserstein matches. So this simple example for biology was was introduced in order to show how from a very simple notion of matching, which we will need in many fields of science to lift some ambiguity, slowly, when you start adding more and more requirements or constraints or flexibility, you end up needing more and more complex tools. All those tools are basically a part of optimal transport theory. Let me just give you another motivating example. This one comes from more like standard vanilla classification. So it's very common when you apply a classifier to a population. So you want to basically predict for a certain person xi some label yi. Okay, and so for simplicity here, let's say the label is going to be binary. So it's going to be red or blue, yes or no, or 0, 1. So this could be, of course, screening for a disease or anything else. So typically, if you do this with empirical risk minimization, you will consider a family of functions that will predict a real value. And then you want basically either that label, and you want that label to more or less match what you have seen in the data. And you would typically do this by minimizing, the notion of loss between your predictions and the actual label. So there's, of course, thousands of references on this problem. But let me try to give you a notion of why this could go wrong potentially in some cases. So imagine you run, your, let's say, support vector machine classifier or any neural net, and you find out, some theta star that is a good function. Basically, what you will do in that case is on your data, you will be producing errors, classification errors for the population that on your training sample. And here I'm just drawing, those circles just depict the size of the error. And so, when you just try too hard to minimize theta star, you just want the sum of those sizes to be small. But since you haven't been told anything else, just do that as in the best way you can. Now, what might happen, and sometimes unfortunately happens, is that by doing this, you haven't realized that some of the errors seem to be bigger in a subset of the population than in another subset of the population. So here you have the purple population, you have the greenish population, and if you actually figure out, look at what happened, well, you realize that the distribution of errors in the purple population seems to be more skewed, towards 0, which means that you're not making that many errors, than the population of errors in the green. And so the goal here is to somewhat enforce some fairness mechanism. So fairness is a very widely, there's several definitions for fairness. So you can come up with your own fairness definition. So this is more like a general statement. The problem that we have with fairness, though, to enforce it, is that fairness is not really something that you can enforce or should enforce at an individual level, but more something that you want to enforce on a distributional level. When you say that a classifier is fair, you're not saying it's fair because it classified me nicely. You're just rather saying that because I am part of a subgroup that maybe was not fairly classified, then et cetera, et cetera. And so here in that case, an important tool to somewhat enforce this and to enforce this distributional mechanism is to use, again, this idea of somewhat matching. And this has been a very fecund, a very rich idea in fairness. And let me explain basically what it would look like. Well, basically, it would say, for instance, okay, I want this classifier to be fair. So maybe after all, what I want it to be is that it should treat more or less similarly people in 2 different subsets that somewhat match. Let's say I have some profile, some template profile in purple population, and I would like to find the same type of profile that corresponds to the green population. So let's say, for instance, take a practical problem. Should I admit some student, coming from to my university? The 2 students maybe come from different countries. And so what I would like to do then is basically try to identify whether this student is like in the top 1% of that university. And if this other student is the top 1% of this other university, although the universities are different. So this is some kind of matching that is going on. And this matching only makes sense relatively to the entire population, right? And so, for instance, this would be like, okay, if I want to make sure my admission policy for university is fair, I could say I want to make sure that the average, student from population purple matched to the average student from population green more or less get the same outcomes. And so this is why, if you look at the literature, you will see a lot of recent works on, fairness and optimal transport. Optimal transport basically gives you this matching mechanism on which you can then define a notion of fairness. And again, this is something that we've been exploring in our toolbox. So yes. Now there's many other examples like this. Everywhere you see data science, essentially, when you don't have the information of who is who, or you need to basically calibrate things, recenter things, do some kind of registration, to use a word from graphics, then you will need someone to run in the pipeline, some optimal matcher that would be able to disambiguate for you the situation. And then on top of that, you can learn and say, maybe, okay, now that I have disambiguated the situation, please learn a classifier for this. And so we have seen this, for instance, in neuroscience. Another interesting area where this has been used, it's in domain adaptation, where there's another notion of disambiguation. You have a training set for which you have labels. Unfortunately, then you train, for instance, a classifier. Unfortunately, you know that you will likely use this classifier on another set of points which do not follow the same distribution, but you could assume at least that the same distribution of labels will be conserved. And so what people have done in this paper called Optimal Transfer for Domain Adaptation is, for instance, try to first find a mapping, a matching that basically says, well, this blue cross here has become a bit like a cell, has become this cell. Therefore, I can, in this area, add a blue cross and then learn a classifier on this new data set, like synthetic data set. So in all of those references, I hope I have convinced you that there's an intermediate matching or mapping step. So for me, matching is really this one-to-one, and mapping would be more like a map that kind of is optimal in the sense that it is able to move an entire distribution to another in an optimal or clever way. The other thing that I would like you to picture is that very often this mapping is not the end per se. This is not really the end goal. Once you have the mapping, it's very rare that you're satisfied with it. Typically, you use that mapping to define maybe a loss or define some next step, problem, then that you want to solve with respect to some parameters. Therefore, if this mapping is intermediate, in this current world, of deep learning, it is very important that this matching process be differentiable. That somewhat you are able to backpropagate some notion of gradient throughout this mapping and the way you have defined this mapping. So if I have to define from those examples a wish list for a matching framework that would work and that would help you, disambiguate that aspect in modern machine learning, I would say that it has to be guided by a rich theory, because we will very likely need a lot of algorithms. Typically, maybe the setups can change very quickly. In some application fields, you will need some type of cost functions to define those mappings. In some other application fields, the uncertainty might be just on the measures that you have. So there's lots of ideas to consider. And so it helps to have, like an overarching principle that helps you unify all this. It has to be very versatile in the sense that this kind of matching problem was used a lot, for instance, as I said, in registration for 3D shapes. But what works for 3D shapes is maybe very unlikely to work for like cells that live in dimension 50. So there are lots of, or maybe the number of points is not the same, etc. So you need to have a theory that is very versatile, and in that sense can accommodate several setups. Another, of course, requirement is scalability. If you're able to match, let's say 1,000 points to 1,000 points, this might be okay for some applications, but in most cases, this is likely to be much more than that. And The other requirement that I'm asking here is this differentiability, because if we want those matching tools to be really used in end-to-end pipelines, then there must be some kind of useful gradient to grab from there. And finally, this robustness is, of course, a practical requirement, but I would also say that it comes from a statistical insight. Essentially, what robustness here means is if you have two distributions and you sample a few points from each distribution and then compute this mapping function, you would hope that if you resample points, the next mapping function that you will get is not completely different from the previous one, right? You want to have some kind of stability and throughout when you do these matchings. And we will see that basically this is more or less all that is needed. And so that theory is basically optimal transport. And I'd say that this is optimal transport with a flavor of, data sciences and machine learning. So as you can imagine, the idea of matching stuff happens everywhere. And so it's no surprise that this theory is irrigating several fields of science and human sciences. And we have to give credit to economists for that, because they are the first ones, with mathematicians specialized in economy, to have understood how important it was, And it's pretty obvious, when you're running an economy or running, a factory, that you have to match, for instance, tasks to workers. And so this is the first thing that come up as a problem. This is an optimization problem. Now, what is really fascinating about optimal transport is that it's not something that actually stayed, in the optimization world or economics world. It has really, really spanned a lot of other very interesting works in both applied mathematics and pure mathematics. So here are two very nice references, and this is like the definite big reference in mathematics. And what is also fascinating from my point of view is that having something that is really beautiful in mathematics is not enough to use it in practice, because there's many considerations that we as machine learners need to cope with, and they come in very different flavors. And again, that might be like the requirement to have differentiability of quantities, the requirement to have scalability, robustness, etc., which are not necessarily always handled, by people that do more look more at the problem from an ideal perspective of knowing the entire shape of your data, for instance, having access to distributions. We never have access to that. So maybe, is there a question? I just want to make sure I'm not. Okay, if not, of course, but please feel free to interrupt me anytime. So the other thing is, why is it really that popular? Well, because it is, a construct, a field that is feeding itself from different areas. And so it's actually very interesting from someone that comes from, let's say, algorithms, to actually look at what people are doing in the theory side. So just as it is very interesting for people that theory to look at how people are using those tools in applications, for instance, because it gives them a sense of, confirming their intuitions. And of course, applications and algorithms go pair in pair, because typically applications will demand more and more efficient algorithms. And what is also fascinating about applications is that they open up new perspectives. And there's this really nice feedback loop that is going on in the last 10 years or so. So the field, just to be brief, was launched by a French mathematician called Gaspard Monge. And the reason it started, gaining popularity, because what Monge did was basically forgotten for a long time, because it was just too hard to solve. But this was basically changed with the work of those researchers here. Two of them received the Nobel Prize, Kantorovich and Koopmans, and of course the work from the huge, George Stanzik, whose introduction of the simplex algorithm solved linear programming. And then what happened that was really also very interesting to see is a wave of pure mathematics results on optimal transport, and some of them really 20 or 30 years later actually bringing very interesting developments in the field of machine learning. I have in particular in mind the work by Brognier, for instance, whose theorem I will explain later. So from the point of view of data sciences, essentially optimal transport is usually advertised as the way I just mentioned it earlier, this idea of optimal matchings, but it's also a way to basically define the geometry through this optimal matching between probability measures. Essentially, when you're able to match the two measures or the two sets, etc., the cost of that optimal matching is what you will use to define how far those two sets are. So let me be concrete. Imagine you have two word clouds and you want to quantify how far they are, how semantically different those two word clouds are. Well, typically what you will do is use a distance function between each pair of words. This will inform your matching cost. And then you will just run the optimal matching machinery to compute basically how this word could be interpreted as being basically this one, etc., trying to find the best possible way to match them, and then compute that cost or use the matching. In brain activations, this is also what I told you. You have two brain activation maps from two different people. Maybe you might want to find out how different they are. And for this, you will use the geometry, the cortex, the notion of distance between this area, let's say, of the cortex, and this area of the cortex is was going to define the notion of distance between two potential matches. And for color histograms, here it's even maybe more intuitive. If you have two images, this is a fairly low-tech way to define distance between images, but it can be quite efficient. It's to basically look at them as distribution of colors and then try to see how you can match those two distribution of colors. And finally, there is another application, which is generative modeling, in which you have a manifold of generated images, let's say, and you have your true data set of images that is lying here. And then you will try to essentially try to match this continuous manifold to the blue point, to the set of the data set that was given to you to learn. So I will mention this a bit later. So this is basically the starting point. So the outline of this course will be to introduce you to the ideas of optimal transport with more mathematical rigor. And then I will show that essentially there's like a different, either you actually stick to the original definitions of optimal transport the way they were defined by Kantorovich notably, or by Morge, and this is going to be the computing optimal transport exactly, or you basically try to fulfill the list of requirements that I mentioned earlier, which was dealing with this idea of scalability, differentiability, and robustness. And I will try to make a case that there are some better estimators out there to solve this optimal matching problem. So if there's no question, let me just start with the introduction to optimal transport. I will try to make it as intuitive as possible using some simple animations. And I will essentially describe two canonical formulations of the optimal transport problem. One which is attributed to Morge, hence the Morge here, and one which is attributed to Kantorovich. And you will see they're essentially the same thing, very close to be the same thing. And at the intersection of the two, you will find the optimal matching problem. And then to close this introduction, I will try to give you an intuition of why optimal transport as a geometry is such a new problem. So are there are there any publications which use optimal transport based methods for evaluation of detection models instead of standard RU? This is a good question. I think people are indeed exploring this. So this is some. I am aware of some works that are going into this direction. Can optimal transport be used to measure image similarity? Is it not feasible? I would like to say probably not, in the sense that if you want to, well, it depends. If you have very simple, let's say, monochrome images like MLSS digits, it can. It's as if you were basically morphing shapes from one to the other. You're seeing one shape as a bunch of pixels that move to another bunch of pixels. And then it makes sense. But for true images, I would say that optimal transport is not really useful, and you should probably use more evolved tools such as featureization. What is the trade-off between optimal mapping, matching, and cost? So I'm not sure I understand the question. The cost of what would that be? You mean the cost of computation? If I could use for similarity, what is the difference between these measures, cosine, Jacquard, etc.? So I will try to give you an intuition for this. So, okay. So this starts with this guy in 1781. So the paper is basically written by Gaspard Monge. Gaspard Monge is a very famous mathematician. So one of the nice things about Gaspard Monge, as you can see, is that as a scientist, he survived the French Revolution, which was not obvious because several of them got their heads cut. And so he then went on to be quite active in the Napoleon administration, created universities, etc. So I'm sorry, I'm looking at the questions now. I will get back to the questions later. So if you don't know about Monge, well, if you go to Paris, you will be reminded about his name, because you will see that there's a few areas of Paris that are named after him. There's a famous place, there's a metro station, there is a street, etc. And so the work of Monge in 1781 starts by the following problem. Is really guided again, and this is what is nice about optimal transport, which is that at the bottom, it is really motivated by a very physical intuition. He basically says, sometimes in public works, you have some earth, some material that is in some configuration, and you want to move it to bring it to another configuration. So one of the typical examples for this is earth, that is, or rocks, let's say, which are in some configuration, and you want to move them to build up some structure, some fortification. And so let's take this example. Imagine you have, for instance, this is like a red pile of earth that is available somewhere, and you need to fill up a hole which is somewhere else. And so then you can ask yourself, what would be an optimal way to move this pile of earth here in red up to the site where you need to fill up the hole? And here I'm assuming that those two things are equal in volume. And if you were to ask someone today, of course, how to do this, it doesn't sound very complicated. It sounds very simple. You would just simply brute force, the problem by just pushing, the mass, so that gradually the hole is filled. There's no thinking involved. In 1781, however, you can assume that this was not so easy. And therefore, you could, for instance, imagine that a worker would need to take a shovel, take some earth at each location on the real line here, R. Okay, so each location here, X, is indexed as a location in the axis R. And if you give an order to that worker, it could be, for instance, take whatever sand is available in the location X in the original configuration and bring it, and this is you are defining here the instruction, you are defining this function t, bringing to t of x. And so the worker would therefore take this infinitesimally small amount of sand at a point x and bring it to a point y on the same axis, which is t of x. And you have the freedom to choose the function t. Okay, you are defining basically a function t which goes from r. Oh, sorry. A function t that goes from r to r. Okay. Now the problem is whenever you are asking the worker to do this trip, of going from x to t of x, Well, it's important to take into account the distance that was traveled there, because of course for a worker it would be a lot more painful to bring that amount of sand throughout, like let's say 20 meters and 1 meter. And so what Morse says is, let's quantify the amount of work asked from that worker at that point here in X as the amount of sand multiplied by the distance. Okay, so that makes sense. This is a bit of energy. And now what you want to find is a function t that is clever enough to do this by not spending too much time or energy on it. And so what is an important requirement for that function is that it has to map the red area to the blue area. And by mapping, here, let's be a bit more precise, I'm saying that for every segment on the real line where there is some mass that you need, so here this blue segment here, you can actually, given a map t, find out what is the source that was distributed into that segment. More precisely, you can define t minus 1b as the entire set of x's such that tx lands in this b. So let's take an example. Let's assume that my map t was doing so in the following way. It was basically throwing points here, let's say around here, maybe some points around here, basically here, etc., etc. But all of them basically, the segments A1, A2, A3 were distributed onto the segment B. Now, what you need to make sure that red is mapped to blue in a precise way, exactly, without bringing too much or not enough earth at that area, is you need to ensure that the amount of sand that is available in those three segments A1, A2, A3 is actually equal the amount of sand that you need to fill in the area B. And so this equality is basically what you would say ensures that at least the mass was conserved between this part between mu and nu as far as this segment B goes. And of course, what you want to do this is you want to do this for every possible segment B. And when this is guaranteed, where for every segment B, you can say that the red measure at the inverse set of the B is equal to the target measure at B, then you are happy. You have fulfilled your goal of finding a map that helps you send the mass from red to blue. So this is some kind of very general form of matching, a functional matching. A functional matching in this case is what is called a push forward. Basically, functional matching is going to be a function t such that you are able to guarantee that you can recreate the blue measure out of the red measure simply by applying t on every point. And so the notation for this is typically the same. The push forward of t, of the measure mu, and the action of t recovers the measure nu. Now, this is not what Monge is asking. Monge is asking, I need this for sure, but the question is, am I able to find one that is actually optimal? And optimality here is going to be finding such a section, such a set of instructions t that minimizes, sorry for this, that minimizes the integral of all the small distances that you're traveling times the measure at each of the point x of the starting measure. So this is what is called the Monge problem. So Monge wrote it very clearly in that paper. He actually proved a nice result on the fact that if your cost was really the distance between 2 points and not a more exotic function, just the distance, then he proved some kind of principle that the matching lines could not intersect in 2 differences. But he didn't make a lot of progress. And the main reason is that this constraint is actually quite ugly. It is very hard actually to ensure that you can find a map T such that T sharp mu is equal to nu. Let me just look at the question for a second. So optimal transfer, we are learning mapping from X to Y. So can we say it's similar to deep learning? Yes, although here, what I would like to insist on is that the difference between a general way of mapping stuff to stuff, as you would do in deep learning, and optimal transport, is that in optimal transport, you have the idea that you have seen stuff on the left, you have seen stuff on the right, and you really want somewhat to find the notion of balanced matching. You don't know who should be matched to whom. You don't have supervision. You don't have, xi, yi pairs. Just based on the distributions, you want to infer a mapping, and you want to infer a mapping that is going to be somewhat a bit optimal in the sense that it is minimizing some form of energy. If I understand your question, in deep learning, very often want to learn mappings x, y, but in that case, we don't have to deal with the ambiguity of knowing who is matched to whom. We just have, training data xi, yi, and then we just try to find f theta of xi is more or less equal to yi. Here, optimal transfer is basically going to solve for you the problem of which xi you should map to which yi. Can this be used to capture servo-native human language artifacts between two sets? I would say that optimal transfer is not that subtle. It's something that is quite low level, and is something that is going to be used really within a more complex architecture. So if you're really trying to do something more complicated, it is very often going to be the case that optimal transfer is going to be just a very particular, low-level component, just as a dot product, let's say. And then the complex thing that you want to achieve is going to be obtained through more things. So in transformers, for instance, there is some form of matching going on. It's usually done using a simple softmax. People have been considering transformers that use type of optimal transform matchings, for instance. What is the trade-off between optimal matching and computational cost? Well, of course, matching is actually a problem that is relatively well understood because this is just samples. Optimal mapping, learning a function is much, much, much harder. But then I would say it doesn't have a very clearly identified computational cost in the sense that, of course, there are some theoretical studies, convergence, etc. But if you want to do this, for instance, let's say with neural networks, I would say the computational cost is not so clear to me. I mean, it really depends on how flexible you want the mapping, the set of mapping functions to be, how large would it be, etc. What's d exactly here? D is just simply the distance. So it could be, let's say, d x, y is equal to the absolute value between x and y, let's say. Or you could use any other, you can use several other distances. It turns out that Monge was, in the example of Monge, d was this, or just simply this, which is just simply, the squared Euclidean, the Euclidean distance. So with that being said, fast forward 150 years later, Kantorovich, Tolstoy, Hitchcock, people that in the 30s start to think about moving things optimally again. And I don't need to explain why. Well, yes, I really use that. Typically, people start really being mindful about optimality when, one, they have the ability to actually carry out that optimality or the policy. So this is typically easier in a centralized economy. So if you are in a communist regime and you are actually not leaving anything to free markets, it's easier to impose a way to move things around that is not going to be changed by local forces. And so therefore it's interesting to see that those ideas kind of started arising in the Soviet Union. And at the same time, they also started arising in the US when people started running into this war economy, which is also a very centralized type of allocation. So in both cases, people start to ask, okay, I have some stuff in some location. I have some other stuff in another location. What is the best way to move it? And let me just try to grab an example from the years around Kantorovich, and I will take one example, which was, for instance, the Battle of Stalingrad. And this is actually a problem that I think was important even to the current time, which is how to move soldiers when you are in a war situation. So imagine this is the front line between the Red Army and the Wehrmacht, and you are here with a garrison, let's say a barrack of soldiers. So let's say those are 60,000, 90,000, and 150,000 soldiers. And you are fighting, and you need a few of them to be on the front line because you have information. And you know that you want maybe, let's say, 120,000 soldiers here, 90,000 soldiers here, and 90,000 soldiers here. And you want this to be achieved as quickly and as efficiently as possible. So in that case, you have to ask yourself, how do I allocate, basically, who I send to whom? And here you can see this a little bit, again, as a matching problem, but a more general one. It's going to be some kind of matching problem because, of course, for each soldier that is in each red barrack, you're going to assign that soldier one particular post in the front line, right? So the French version of this story that I could use as well is this idea of having restaurants, and the restaurants are actually using baguettes every day in a varying number, and then you need to travel around Paris to bring the baguettes from the bakeries, let's say, to the restaurants. So as you can imagine, there's like countless variations on this story where stuff is available somewhere and you need to bring it somewhere else. So if you are a Red Army general here, you know that you can move your troops along some roads. And of course, as you can see, some roads are longer than other roads, right? So it takes, of course, longer for these soldiers to go here than for them to go from here. But still, you can't actually just simply send everybody to the nearest front line, because in that case, you would get something that is not balanced. If you want to send everyone to the nearest one, you get 60,000 soldiers here. Let's say, if you wanted to do this kind of naive nearest frontline assignment, you would get 90 here, which is fine, but here you would get 150. And this is not what you want. So you need to work a bit harder. So there's one very, very simple way of actually achieving this. And it's a way that is very naive in the sense that it doesn't even look at the problem, but you can actually formulate a possible answer, which is, well, notice that I need 120, 90, and 90,000 soldiers here. That means that for every 4 soldiers that I will have here, I will need 3 here and 3 here. So I have basically a proportion of 4 to 3 to 3, 40%, 30%, 30%. And to reach that, then therefore you can just simply split your troops into 40, 30, 30 at each of the barracks. This is what I did. And you just send everyone, traveling around. And then you have this huge network of people crossing each other because you've splitted, the barracks according to the target distribution. And so I would like to just say 2 things. This is nice because you always have a solution. There's always a naive solution. You don't really have to think too much about it. There are usually other naive solutions as well, but this one is a simple and intuitive one. The solution did not even look, at the problem. How far is basically each barrack from each front line. And so in that sense, if you wanted to think a bit in terms of robustness, this is the maximally robust solution. So let me just maybe state this differently. Imagine now you are, the other side, you're in Germany. If you find out that, some of the roads are important for your enemy, to communicate, to send troops around, then maybe you might want to, let's say, bomb this road, let's say. And then in that case, because the adversary here, the Red Army, didn't really take into account any optimality, well, intuitively, the fact that this thing here is blocked is going to remove maybe a part of the soldiers here. But overall, you will have a solution that has kind of worked okay. So by this, I want to say that the naive solution sometimes is also the most robust. And this is related to something later that I will mention, which is when you want to couple 2 probability distributions, the so-called independent coupling, the product of the 2 distributions, is naive but useful coupling. And this is used in something called MMD, or maximal mean discrepancy, or energy distance. So here in this story, we are not going to try to be blind to the problem, and we're going to actually try to find the best possible solution. So let me just walk through the linear program that is going to be involved in optimal transport. So the first thing you have to notice, of course, is that the problem itself, if you forget about all those pictures, it's essentially characterized by two things. On the one hand, this is the input and the output marginal. This is the first and the second marginal. This is what the configuration in the beginning and the configuration in the end. And the other important information, of course, is just simply the distance matrix or the cost matrix of moving a soldier from each of the blue barracks to blue front lines to the red barracks and vice versa. So this distance matrix here is essentially the only thing you need. And the only thing you are seeking and you want to understand as a general here is just simply how much soldiers should this barrack send to the first front line, the second front line, and the third front line. So once this is basically, we've understood that the problem, the abstraction of the problem is just about these two things, marginals and cost, then you can basically go on and solve it. So this is going to look a lot like the Morse problem. You're going to say, well, I want to find out a set of instructions. Unlike the Morse problem here, the set of instructions is not x t of x, but it's going to be more like one barrack, several potential front lines, and then I need to specify the proportions. And so I will call those cells P1A, P1B, P1C, etc. Those are, I'm just going to use slightly shorter notation saying that those are the histogram values. And if you look at what a valid transportation plan will look like, it's going to be a lot more simple than the Morse problem. In the Morse problem, remember, you had this like push forward constraint, which was actually a very abstract kind of matching constraint. Here, it's going to be a lot more simple. It's going to be simply, when I have a matrix, I just need to ensure that when I'm instructing, those soldiers to go to A, B, or C, the number of soldiers that is going to go to A, B, or C from 1 has got to match with the number of soldiers that I had initially at the first barrack. And the same thing applies vertically and horizontally. So we will have row sum constraints and column sum constraints. This is a bit what I wrote here. The sum, if you sum for every I the j's, then you will need to recover actually the input. And if you sum the columns, you need to recover the output. So it's a very geometric, very simple problem. And then the cost function is going to be, again, inspired by Morse. It's just going to be, well, if I am sending that many soldiers from between I and j, I will pay a cost which will be proportional to this times the distance. So therefore, here your cost is the same a bit as the Morse. Cost times quantity of goods traveling between those two segments. And so the problem is going to be just simply minimized over a lot of matrices, the cost of that matrix itself. So let's take a look. What would look like? Well, it would look like this. It would basically be, okay, I'm just going to split a bit, not as much as before. Visually you can very clearly see that it's not the same, wild splitting of people traveling in all directions. It's going to be a sparse matrix. And this is where we're going to see later. So I hope I have more or less given to you a bit of intuition of those two problems. When you look at the Morse problem on the top left here, you should basically imagine that this looks a lot like comparing continuous distributions. So the Morse problem itself is kind of the reference when you have in mind continuous distributions. This Cuturi problem is more the reference that you should have in mind when you're thinking about comparing samples, point clouds, discrete measures. And then there are some interesting interactions between the two. And so this is more some of the results are more mathematics in nature, but some of the results are actually quite applied. Let me just maybe finish with yet another nice interpretation. And this is, again, an interpretation that goes a bit along the lines of this genomics application. In both the Morse, I had an issue with my computer. So in both, you hear me well, yeah? So in both the Morse and the Cuturi problems, I hope you have felt that there was the knowledge of what stuff was in initial configuration and the final configuration, and you had the freedom to choose how to move the things. So this is a bit the active perspective on optimal transport. There is a more passive optimal transport perspective, which is the one that is in the genomics problem. And this is one that is highlighted by Alessio Figali, a Fields Medal 2018 for his works on optimal transport, which is that optimal transport, or this optimal matching, can also be seen when you're solving the problem as what would be the nature's way of moving particles if I don't know anything else. So if, for instance, you're giving a cloud of particles in some initial state and another cloud of particles in another configuration, but you're not able to pinpoint who is who. So optimal transport somewhat gives you an answer. It tells you, well, if you have to figure out who went who again with the cells, the most maybe likely answer is the one where nature has used the least energy, and therefore the solution of optimal transport is the one that could be a good guess. So this is a slightly different perspective. So now let me dive a bit into math now, a little bit of formulas. So this is not the most general formulation of optimal transport, but it's one that will be useful in most cases. Suppose that you have a measurable space. You have a cost function that will take 2 points in that measurable space, and you have probability measures defined on omega. So if I go back to the Monge problem in 81, the abstract setup of Monge is find a map that goes from omega to omega, okay, that maps x to t of x, such that this is an important constraint. I recover, this blue measure by applying t on every point of the red measure, like moving everyone, and I am minimizing overall the displacement energy. Okay, the entire displacement cost. So, as I said earlier, 1781, this was published. For a long time, this did not really actually arise the curiosity of fellow mathematicians. And then we had Kantorovich, and then we had people that restarted discovering this problem. And then there was a very fundamental result. And this is, of course, plus 87 plus 200 years. Okay, 1987. And then we had this beautiful result by Brognier. Other people were coalescing around the same ideas, but it's usually we attribute it to Brognier. He said the following, and this is really a beautiful and deep result. He said if omega is the RD, okay, so we're pretty happy with RD, usually in machine learning, and the cost is the squared Euclidean distance. Again, machine learning, we like the squared Euclidean distance typically. Then if the two measures are not pathological, so for the purpose of here of this slide, I would just say they're absolutely continuous with respect to a Lebesgue measure, then T, the T star, so I should probably put T star for this to be meaningful, the optimal transport between the two distributions has got to be, it must be, the gradient of a convex function. So this is beautiful in the sense that, okay, remember that if I say that U from RD to R is convex, okay, then I can basically write, of course, the gradient of U. The gradient of U, remember, is a function which to a vector associates another vector, okay? So therefore, somewhat a gradient of a convex function is already of the type of problem, of the type of family of functions that I'm interested in. The gradient of a potential is a function mapping a vector to a vector. Well, what is really, really mind-blowing about this Brognier theorem is that it tells you the only way a mapping T between two measures can be optimal is if it's the gradient of a convex function. Again, here I just want to stress this is valid in this case and this case. So Monge's problem was very, very general. Here, this is substantially narrower, but it's a really huge step into characterizing what optimal transport looks like. And if you actually look a bit more into the results that Brenier proves, he says a few other things. He says that if there's any function u that is convex, then whenever you're going to map, basically make a measure mu move along its gradient, then this displacement is going to be the optimal transform map between what you got after moving and before moving. So this is a bit subtle, but the idea is basically gradients of convex functions move stuff optimally in terms of optimal transport distances or cost in a square Euclidean sense. So this has been used recently in a few machine learning papers, but this is just a few months old. This was used about 1 year ago. No, sorry, in December 2020, and I will refer to this reference later, and connects a bit the literature on optimal transfer with normalizing flows. And the reason this is actually a very, very powerful statement, I will just very briefly mention this, is that I didn't mention it before, but basically the push forward constraint essentially tells you that you need to have a change of variable formula when you apply t to the first distribution mu and recover nu. So it basically says that you need to have that for every point x, that the density p of x, so if pq is the densities of mu and u, that the density of p of x has got to be the density q computed at t of x rescaled by the determinant of the Jacobian of that map. So this is the change of variable formula. Now, what is really beautiful about the Monge, the Brenier theorem, is that, remember what I told you is that if t is optimal, then it must be t is equal to gradient u for some u convex. Okay, there must be a u convex such that its gradient is equal to t. So let's replace just simply t by u, and this will basically give us a different change of variable equation. And this is exactly what you get. Here, if you replace the Jacobian of t by the Jacobian of the gradient of u, this is called the Hessian. So I'm sorry, I should probably write f and not u. So if I just wanted to write it in using my notation, I should probably write u and u everywhere instead of t of f. So basically, you would just want to solve this change of variable formula, but knowing that the mapping function here, t, is the gradient of a convex potential u. And this equation here is called the Monge-Ampère equation. And Figali, in part, got his Fields Medal for work on this Monge-Ampère equation. I won't dive too much into this. Oh, okay, sorry, I'm sorry, just do that. Sorry, but many students have problem with video and audio latency. Could have a short break to let the staff fix this problem. Yes, sure.
Yes, we take a break. So
Okay.
We'll take a 10 minutes break.
10 minutes, perfect.
Thank you.
I'm happy to take questions if people have them in the chat.
start, we still have a countdown, right?
Yes, we have countdown.
And after the countdown, I think Dr. Marco, you can directly start. And
Sure.
actually, there are some questions from the student. Mingyang, you can.
Yeah, I will pass it after it starts. Yeah.
Yeah.
Oh, now.
There's some question during the break time, so you can carve it into the children. So probably Dr. Marco, you can answer when you start the presentation. Thank you.
So 30 seconds. Ten seconds. 5, 4, 3, 2, 1. Start.
Okay, so we're back. First, I'd like to just look at the questions from this lecture. I think reinforcement learning algorithms can solve optimal transport problems. I'm not sure what you mean by that. It's not completely obvious to me how you could basically, I mean, if by this you are saying that you can learn how to solve a family of transport problems that you see repeatedly, then yes, I guess you can try to learn by supervision some form of machine that can spit out an optimal transport. But one that actually is doing this for any configuration of the data, it's not obvious to me, or maybe I'm not understanding part of the question. Please, can you say something about the application of our algorithms in deep learning to optimal matching? So it's very, this is a very open question, because if you mean by deep learning just simply the idea of minimizing the loss of a function through gradient descent, that function being a composition of elementary functions, then there are indeed approaches to do that using deep learning. For instance, one of the recent trends is to use something called the input convex neural network family to then parameterize the functions that you are seeing here on the slides, which are convex, and then to try to minimize them. And I will mention this a bit later in the literature. So this is something that is relatively recent, maybe 1 or 2 years old. It's not completely well understood whether this is doing what it's intended to do because of the usual issues with deep learning and instabilities, but there are people that have been looking into this. In slide 44, what is exactly transposition matrix in calculating the cost function? So here there's no transpose because there's no. So is there a transpose here? What exactly is the transposition matrix calculated? Well, basically, you're going to sum this times this plus this times this plus this times this, etc. So you just collapse. It's a standard Frobenius dot product between matrices. Just to go to the equation P equals X, so type for improper informative price and Bayesian problem, but now Tx is given and Qx, Px, it's solved for Px. On high level, this looks a bit like the inverse of motion. Yes, this is true. The soldier moving example, the two probabilities share the same supports. What can the supports are different? Yeah, so exactly. One of the important things I think to understand is that in this case, it's as if you had two probability distributions that are supported on different sets. One probability distribution, the red measure, is basically supported here, and the blue distribution is supported here. And the way we are still able to compare them, and this is probably what sets optimal transport distances apart from the other usual Kullback-Leibler divergence and things like that, is that essentially you are going to use the idea that you can travel from this for each of the red to each of the blues. So unlike, for instance, F divergences that never use the metric structure of the base space, the very defining feature of optimal transport distances is that they use it. They use basically, if you're comparing let's say, a P of X with a Q of Y, a typical F divergence would basically be some kind of function which integrates a difference between F of X and, P of X and Q of X integrated across the entire space. Here we are going to allow ourselves to move a little bit the masses, to somewhat disambiguate a bit whether we can find a way to move the masses of the first measure to the second measure to make them map again. Whereas an F divergence or Kullback-Leibler or L2 is just going to look point by point on the entire space. What is the difference between P and Q? And this is a notable difference, and it's one that basically also energy distance tried to take advantage of. But as I told you earlier, the energy distance, and I will say it again, is a particular case of optimal transport in which you're using this very naive transportation coupling that mixes everyone with everyone. In CV, we have one distribution. In CV, I'm not sure what CV is. Maybe cross-validation. Yes, actually. So here you're asking a question, which is, imagine I have a big bunch of data, and I subsample two different parts of that data, and then I try to use optimal transport to compare them. And you're asking, will it work? I'm guessing the question is, will it be useful to do that? And actually, I have an example recently of work where we try to do this to impute missing data. So the idea is, imagine you have a bunch of data, some values are missing. The main assumption here is that you want to find out guessed values that are missing. So what you could do is take subsets of those two big data set with holes and try to minimize the Wasserstein distance between them. So that's a bit the idea. So let me just move on to sorry about this. Move back to here. So this is just a mention to the links between the Moore-Jean-Pierre equation and optimal transport with the square Euclidean distance. The Moore-Jean-Pierre equation is essentially an equation which is studied in PDEs, in partial differential equations. So here it seems that there's a very strong link between the function f that is going to be convex, and somewhat here you want it to be because you want the Hessian to be strictly positive definite, and resolving that PDE and actually finding an optimal transport from a distribution P to a distribution Q. So one of the reasons, though, this Morse formulation is not so easy to manipulate when you're dealing with finite data, and really fits well the continuous data set, the continuous distribution framework, is that the Morse problem is not well posed if you're actually studying discrete measures, Dirac masses. Let me just give you a very simple example. Imagine you have an infinitely concentrated Dirac mass. This is your Earth, which is somewhat available to you in a very long pipe at one point x. Well, if you're asking a worker to move that pipe, that infinitesimal pile of sand, which is very tall, and you're only asking the worker to move it from x to t of x, then the only thing you can recreate on the right-hand side is going to be another big pile of sand, right? There's no way you can actually do something as beautiful and complicated as this pile of sand by just pushing forward this Dirac. Whenever you push forward a Dirac, you will basically get another Dirac, which will be just simply d of t, delta of t of x. So therefore, if on the left you have something that is not very continuous, and on the right you have something that is very smooth, there's no optimal transport that can actually, there's no transport, there's no push forward that can exist between left and right. Of course, this is very asymmetric. In the other direction, you could basically pile up everything on this pile of sand if you were just trying to solve the problem the other way around. So from this problem, I guess you can see that there is a simple workaround, which is the one that was already introduced in this idea of soldiers, that move that are free to split a bit themselves across different front lines. We were not taking an entire barrack and moving it entirely to one front line. We were splitting the mass. And this is what makes it easier to solve the problem. So instead of basically asking the worker to take the sand at x and bring it completely to only one point y t of x equals to t of x, we are going to allow the worker to somewhat, spread around a bit of the mass that the worker was able to find at one point x. And in the probabilistic language, what this essentially means is that you will have a probability distribution for each point x that you will pick up. You will have a probability distribution where you can spread out, the mass proportionally to that probability distribution. And so this means that essentially we will have this conditional distribution for every point x. And when you glue together all of those conditional distributions, basically what you get is a coupling. And what is important to notice is that too much like the Cuturi example where we had the soldiers and the barracks, etc., we needed that the matrix had the row sums and the column sums that were actually agreeing with the input and the output distributions. Here in this case, we just need to have a coupling, a probability distribution of square space, or omega times omega, which is going to be such that it has exactly the right marginals, mu, and nu. So mathematically, what this means is that if I take any subset of omega and I compute the total volume, if you want, the mass of P on A cross omega, then I get mu of A. And if I do the same thing with B, I will get nu of B. So maybe it's easier to look at this visually. Imagine here omega is R. We are dealing with the real line. We have two distributions. One here is mu, okay, and one here is nu, okay. So this is probably a bit wrong. This should be x, and here this should be y. Two distributions. What is the coupling in this sense? Well, it's going to be a distribution on their square. And what is the coupling with the right marginals? Well, it's basically something where if you sum up, if you take the integrals in this, if you marginalize, then you get the first distribution. If you sum up in this direction, you end up having the other distribution. So this is what we're going to deal with. And it's very immediate to see that whatever the distributions that you give me for mu and nu here, I will always be able to find one which is going to be satisfying those marginal requirements. And that's just simply basically, let me just write it. It's just going to be something like P of x, y. If I have to write its density, mu of x times mu of y. It's just as easy as taking the independent coupling. So there's always going to be a coupling, but here there's actually many of them. It's actually quite easy to create some of them. And so here's another one. So essentially, if we take a step back, from the simple toy examples with the soldiers, we can now define this Cuturi problem, which is the continuous, description of the soldiers problem. We are going to integrate to take across all possible couplings that have marginals blue and reds. The one that minimizes its cost, and the cost, remember here we had written like something like sum of P ij d ij across all possible pairs of barracks and front lines. Well, this is the same thing except that I'm using a double integrals term. That's it. There's nothing more really going on. So this is a very generic definition. Here we have the primal formulation of the Cuturi problem. This is de Monge. And we have the two canonical optimal transfer definitions. An important thing, though, that I want to stress, this, in terms of constraints, is pretty ugly. This push-forward constraint is really, really actually pretty hard to deal with. And most importantly, it is not a convex constraint. In the sense, I mean that if I have T1 push forward mu is equal to nu, T1, T2 push forward mu is equal to nu, then this in general does not imply that for lambda belonging to 0, 1, lambda times T1 plus 1 minus lambda times T2 push forward mu is equal to nu. So you don't even have to deal with, you cannot even deal with a set of convex set of functions. which makes it very, very hard actually to solve. On the other hand, if we look at this thing, essentially this constraint of having a marginal, which is mu and marginal nu, is actually a linear constraint. It's very easy to see that if P1 belongs to pi of mu nu and P2 belongs to pi of mu nu, then their linear convex combination is going to also belong to pi of mu. This is just because essentially the marginal constraint is just a linear constraint. It's just saying if I'm adding in this direction, I get this. So indeed, if you just take two things that added in this direction recover the right marginal, if you just mix them in a convex way, you will still get the right thing. It's very easy, to play with distributions if you just take convex combinations of them. So this is a linear constraint, and this, in terms of as far as P is involved, this is also a linear function. If I take P1 and P2, if I just integrate P1 against C and P2 against C, then if I just take the linear combination, it's going to be the same thing as combining those integrals. So this is a linear objective, which again, also this is not. This is a linear objective. This is a linear constraint. This is what is called a linear program. And this is arguably one of the most understood, type of optimization problems out there. And if you know a bit about about linear programs, then what you know is that whenever there's a primal problem, there is a dual problem for this linear program. I'm not going to mention too much duality here because it would take maybe too much time, and I won't be able to cover other more exciting things in the end. But let me just basically restate this from an applied perspective. Here, this is an optimization problem where you are optimizing over a space of couplings. So space of couplings is very large, it's omega times omega. And you're studying couplings that have this constraint of marginals that kind of match their data. And you're integrating against something which is the cost function. So the marginals are in the constraints, and the cost function here is in the objective. When you study duality is a very convenient way to kind of flip whatever you had in the constraints becomes something that appears in an objective, and whatever you had in the objective becomes something that you have in the constraints. And so it's not a surprise if this thing here, the cost, is now appearing somewhere in the constraints, and these two things which were in the constraints for the couplings now appear in the objective of this dual problem. And what is the dual problem? The dual problem says the following. This problem here is equivalent. It's equivalent in the sense it has the same objective than the following problem in the bottom. And the problem in the bottom is the following. I'm going to consider two functions, real valued functions in the space omega, phi and psi. And I will try to come up with a pair of functions phi and psi such that the integral of phi against the first measure and the integral of psi against the second measure is as large as possible. Of course, if I only say that, you just set phi and psi to plus infinity, and then you get something that is super large, because mu and nu here are positive, so you're integrating against something positive, so you can make it as large as you want. But the catch here, of course, is that there is a constraint. And the constraint is this constraint, which is that for every pair of point x and y, you need to ensure that phi of x plus psi of y is smaller than the cost of going from x to y. So this is essentially why Kantorovich got the Nobel Prize in economics. He's the first one to have really posed, duality, introduced duality to the optimization community. Now, sorry, I could derive Kantorovich duality, but I think we will run out of time. So please look at the slides if you're curious about trying to understand how we get there. But this is just simply very, very school, very, very elementary linear programming duality. But I would like to say that this duality will play a role later. And it will play a role later because sometimes it's easier to optimize on the space of functions than optimizing on the space of couplings. I think there is a question. Oh yes, sorry. L1 here is let me just not do the animation again. Okay, did it? L1 here just means that it's integrable. You can integrate phi against mu and psi against mu. So it's a bit pedantic. Maybe I should remove it because it's pretty obvious from the context that you should be able to consider, that you should consider functions that can be integrated. Now, let's go now to the one of the objects that you will find a lot in optimal transport, which is this idea of Wasserstein distance. So in fact, the Wasserstein distance is just the output of this optimization problem for a particular class of problems, which is when the cost itself is a distance to the power p. So p is just an exponent, a bit like a q norm. You know, when you define x minus the q norm of q is equal to the sum of xi power q to the power 1 over q. Okay. Well, the p here is really the same thing. It's just some kind of trade-off between whether you want to consider outliers, be quadratic, etc. And as you remember, there is one important case where p equals 2 helps us, and the distance is Euclidean distance, and that's the Prunier theorem. And p equals 1 is also the case that was historically considered by Morse. But the more generic definition, and one interesting thing about this definition, is that for every p that is bigger than 1, if you compute the optimal transport cost between two measures with a cost which is the distance to the power p, and then you just take the power of 1 over p of this result, then you get something which is a distance between measures. And this is not, I mean, trivial to say, because it basically says that whatever the p, this thing here will satisfy the triangle inequality, will be 0 if and only if mu equals to nu, etc., etc. So what this basically asks you is to keep track of this 1 over p here. And so what most often people will end up doing is actually forget about this 1 over p and just always write wp to the power p. A bit like when you write xq to the power q. Okay, you kind of get rid of the you get rid of this. Okay. So this is the Wasserstein distance. And so when you hear about the Wasserstein distance between measures, this is what we're talking about. Now the reason, so this is why, okay, we go to the L1. The question by Ola was basically, what is this L1? This is just a way to say you can integrate phi against mu. Let's forget about it. So you remember that there is basically in the former definition this coupling definition. And I also told you this very same thing can be computed using this dual formulation. When we are going to find functions that you integrate against mu and nu, for which you want the integrals to be as large as possible when you take them together, with the constraint that this is basically not varying faster, if you want, than the distance. This basically means that if you look at phi of x, wait 1 second.
Sorry, Marco, I think you are muted.
Yes, I'm muted. I just need to take a call for a second. I'm sorry, this was I'm quarantining right now in Japan, and so I get a phone call every day from the health ministry, and so I had to basically just simply say hello, and that I'm quarantining correctly in my place. Sorry. So let me just go back to the point. So when you have this, what essentially this thing is telling you is that phi of x and psi of y are two real values, but they must not vary too much one relative to the other. Meaning, if x and y are close to each other, then you don't expect those two functions phi and x and phi of y psi of y to be very far away. So this is somewhat a constraint, if you want, on when you're going to make this as large as possible, you need to be a bit careful that phi and psi don't vary too quickly with respect to the distance. And the computations, I mean, this gives rise to a beautiful theory in optimal transport called D transforms, or C duality, which is a generalization of convex of Legendre transforms. But the most obvious, I mean, not obvious, but the most direct application of Kantorovich duality is this result that I don't have the time to prove, but which is very important, which is that when the cost is the distance, meaning when you are placing yourself in the Moore setup, then you would typically put p equals 1 here, like here. When it is a distance, essentially, solving optimal transport is the same thing as finding a potential function, which is 1 Lipschitz. So remember, 1 Lipschitz just means that phi of x minus phi of y is smaller or equal to the distance between x and y. So this result is often quoted in the literature. It's not, it takes a few steps to prove it, but this is essentially deriving, from a few other more complex things called D transforms that were developed in optimal transport theory. So let me just, with this, kind of conclude this intro by a few other important results. What is the difference between the Morse and Kantorovich problem? The Morse, you're trying to find a map, and the Kantorovich, you're trying to find the coupling. Well, essentially, they kind of are the same, and one is the relaxation of the other. I hope you got that feeling, that by allowing the worker to spread the sound, we're somewhat relaxing, the problem in a very canonical way, which is rather than enforcing a one-to-one mapping, we're enforcing one-to-many. It's a very standard trick, in optimization. And the nice thing about this relaxation is that when the problem is well posed, the relaxation is tight. So solving the Kantorovich problem is going to be equivalent to solving the Morse problem. There are a few important results there. Let me now try to give you a bit of a feeling of why optimal transport has this very nice, geometric flavor. Suppose I have two probability distributions. One is in this setup and the other in this setup. Those are two Gaussian mixtures. And imagine now that I'm going to compute the Wasserstein distance between them. So remember, in this case, I will need to compute a coupling in dimension 4, one marginal being in 2 dimensions, the other in 2 dimensions. This is a dimension 4. I just run, let's imagine I have access to a universal computation machine that will give me the value of this Wasserstein distance. So this might be the Wasserstein P, let's say the Wasserstein 2 distance, to be a bit more specific. And so this gives me the idea of how far those two distributions are. But the nice thing about a metric, when you have access to a distance, is that you also get access to geodesics. In principle, you should be able to access, a sequence of points in the space of probability distributions that make it, have a shortest path between those two things. And so in that case, you can actually plot this. And this is called the McCann interpolation, because McCann was the first to highlight this. And what you essentially see is this phenomenon where, a bit like the Morse problem, you imagine you're starting from the first configuration, you're ending at the last configuration, you take an army of, let's say, 1 million small workers that each are going to follow your optimal transport map T, and then you freeze them in time as they actually carry out their duty of sending the mass from left to right. And this interpolation is in itself an interesting tool. So beyond even the idea of the notion of computing a distance, or to quantify how two things are different, what is nice about a true geometric framework is that you can compute now basically a true geometric, geodesic between things, interpolations in the sense of finding out the middle point with that metric structure. PMI is coupling similar to a joint distribution. A coupling is a joint distribution. It's the same thing. What does the P mean? P means, in the previous slide, this P meant coupling. So let me try to give you an intuitive example, again, of why the optimal transport geometry is a bit different from anything that you've probably seen before. Imagine so right now I'm in a room, there's an air conditioning unit, behind my back that is spitting out a cold temperature. And then there's a window there, which is basically being hit by the sun, so it's warmer. Imagine during the day, I take 2 histograms of temperatures. And I have 2 sensors. One is in the air conditioning unit or very close to it, and the other is in the other side of the room where the window is. So of course, what you would get is a high histogram of temperatures during the day. Here, maybe this is morning, the morning, then maybe at some point there were some clouds, and then again, the temperature fluctuated close to the window. And imagine I'm taking the temperature sensor here close to the air conditioning unit, which was more stable. So I have 2 different histograms of temperatures throughout the day. Imagine I want to merge them. So what I would like to have an idea of what is the average temperature histogram during the day. And if you do this in a naive way, or interpolate in a naive way between those 2 things, well, obviously the thing that we know how to do is basically take mu, add them and divide them by 2. And so this is likely what this would be looking like, right? So this is something like this. So it would be basically the histogram, which has both temperature distributions together in a somewhat, divided way. They live in different worlds, and we've divided them by 2 and added them. And this is more or less trying to summarize. I've done a sensor fusion, if you want. I've fused my 2 sensors by doing this. The optimal transport viewpoint is going to say something very different. It's going to say, well, I have 2 distributions, the blue and the red. What I can try to do is essentially try to find the optimal transport map between the blue to the red and stop in the middle. And this is precisely what I would get here. This is precisely this thing here, which is my Wasserstein average, if you want, of those 2 distributions. Can you explain why the constraint of phi x plus psi y existed? I'm sorry, I would be a bit short on time if I explain this. If you look at the slides, there is an animation that tries to explain how it arises. Essentially, it is really a duality result. It's really the fact that the cost, as I said earlier, was playing a role in the objective, in the primal problem. In the dual, it will pop up somewhere in the constraints. This is a bit mechanical, but this is the mechanical explanation. Any other explanation will take at least 5 to 10 minutes, so I prefer to let you investigate this on your own, or look at our book. In our book, I wrote, like, I think 2 or 3 pages trying to give an intuitive explanation for the dual problem. So as you can see, those 2 things are completely different. On the left one, we have simple averaging of distributions as if they were vectors. Maybe it makes sense, maybe it doesn't. On the right-hand side, you have a different one, which basically tries to say averages of distributions is you first find a way to move one optimally to the other and then stop in the middle. In some applications, it seems this way of doing averaging is interesting. And you can also, of course, generalize it to more than just 2 distributions. How would you do this? Well, typically when you define this, averages in metric spaces, like means in something that is not a vector space, the way you do this is by saying, well, the average of different things. So here's the new i's, let's say my 3 measures are there. The average of these things is the one thing that minimizes the sum, maybe weighted, of its distances to the original data points. So in this case of vectors and Euclidean distances, when you use a squared Euclidean distance, you recover the usual definition of means. But when you're in a matrix space, you can use a more general notion of means, and this is what you would get. And so here, again, the average of those 3 2D measurements here, if you were to compute it in optimal transport sense, it would be this thing lying a bit in the middle. Whereas if you had to do this in a simple Euclidean sense, you would basically add up those 2 distributions, and you would get something that would look more like something like a big blob, covering all the space. To illustrate this further, let me just take, so is there a geometry associated with taking the average of the histograms? Yes, that's just Euclidean distance. The Euclidean distance is really, the Euclidean distance, the L2 norm if you want. The L2 distance between distributions is what you do when you just take the average. And this very different form of averages is the Wasserstein average. Can you explain Lipschitz condition intuitively? So the intuition of the Wasserstein distance is basically, so this is called an integral in this particular case. So let me just go back a little bit to this thing here. So the question is, can I provide an intuition for this? Well, there is something, a family of distances for measures, which are called IPMs. So we're going to call delta, which is a soup of f, or let me just write it phi here, in some function space of the integral, exactly what is here, of the integral of phi with respect to so this is called an this thing here is called an IPM, integral probability metric. So if you heard about, for instance, MMD, this is an IPM. There are several different IPMs. So what happens in this case is that the Wasserstein distance is an integral probability metric where the family of functions that you're looking at are Lipschitz functions. So somewhat an integral probability metric tries to test how far you can discriminate a measure from the other by using a certain flexibility on the classes of functions. So if you're using, for instance, functions which are in our AKHS, or reducing kernel Hilbert space, which are quite smooth, then it's going to be difficult to discriminate between two measures which are very close to each other. So depending on the class of functions that you're using, you're defining a new type of discrepancy between measures. It turns out that when you use Lipschitz functions, which are actually very well behaved, you get something which is equivalent to Wasserstein distance. And if the question is, how can you go from here to here? I invite you to look at the slides. I think I've uploaded them in the PDFs. If not, I will upload them again. I may not have uploaded this in the PDF. It's true. So I will refresh the slides with a more complete version. Could you explain the connection between optimal transfer and curvature on a high level? This is a bit beyond, I am afraid, the presentation today. So let's say that, so clearly the optimal transport geometry on the measures is not a flat space. It's not a Hilbertian metric. So it defines a curved space on the space of probability distributions. And the other nice results that you have between optimal transport and curvature is that you can basically use how costly it is to transport from some local areas to other local areas by blurring a little bit and relate this to curvature. And so this is something that is known as Yann Olivier's curvature on graphs. And then there's also many other links that kind of go beyond what I know even between Ricci curvature and optimal transport. But if I just may basically say something a bit vague, the reason pure mathematicians use optimal transport in some of those proofs is that because it helps them define some important results on how mapping some sets to other sets and having some regularity conditions on those mappings to then study, to basically translate some constraints on curvature in terms of what the optimal transfer should look like. And this is pretty much the most I can say in this context of the MLSS. So the this idea of Wasserstein distances, Wasserstein interpolations, actually you can start, having fun with it, right? You can start playing with interpolations, because if you're actually able to solve this minimization problem that I just showed you here, you can start, using interpolations of shapes in 3D. And it's as if you were thinking that those shapes are 3D gases, and you can actually try to look at them as densities, and you're trying to find what is the optimal way from this density to go to this other density and stop in between. And you can also do this for more shapes by minimizing this, more than 2 shapes by minimizing this problem. So this is something that we were actually very happy to see working a few years ago, when we were able to solve numerically these optimal transport problems. So this was a long introduction. Let me just try to summarize in one slide where the field has gone and where it's going. I'd like to say that right now I've not mentioned computations at all, and it's hard to actually solve those problems. It's not obvious. It's not always easy. But suppose, we were able to actually find algorithms to do this. Well, up to 2010, the main concern in the, I would say, machine learning / computer vision / natural language processing / data sciences communities in general was to compute the Wasserstein distance. Are we able to actually get this? Are we able to reach the point there where we can compare histograms of large size or measures of large sizes? And I think it's fair to say that for a long time, this was actually quite hard. Around 2000, we were able to start, proposing interesting tools to compute, to solve this. So one of them I will mention later, which is this entropic regularization. But I should say that other approaches kind of started working. And then people started seeing new possibilities. They thought, okay, here is a new distance that can compare probability distributions that I have. Usually in machine learning, the finality is not just to compute the distance, but it's rather to learn with the distance. So if we look at vectors, for instance, it's not so fun or interesting to just compute Euclidean distances. What we use these Euclidean distances for is to minimize them, typically to produce a loss function. And so eventually people started saying, okay, maybe Wasserstein distances are fun, they're nice, we can compute them, we can even start doing averages and things like that. But can we do something more than that? Can we actually learn with a Wasserstein distance, where a loss function between a measure and another measure that I'm synthesizing or creating from some data or is creating as a generative model, etc., is the distance needs to be minimized. And this was the turn, I would say, where people started saying, well, maybe computing this or being able to upper bound it in a fast way is not so fun anymore. What we want to do is minimize a function where there's going to be some notion of measure there, or maybe a parametric measure, and take into account the Wasserstein distances of that measure to other measures as a loss. And if you start looking at this problem, essentially if you just do the chain rule, you find out that essentially what you want to do is compute some notion of gradient of the Wasserstein distance here with respect to mu. And I'm putting quotes because the space of measures is not a vector space, right? So you can't really write gradient in this way we're used to writing it for a vector valued for real valued functions of vectors. And here, what is really fun and interesting in the optimal trans community is to look and realize that actually mathematicians were solving those problems, or started solving those problems 20 years ago. So some of those important, applications, I would say guiding principles on computing the idea of gradient in the space of measures of the Wasserstein distance were laid out by those important works. So let me just, do you have further examples of this application, maybe in engineering fields? You mean the 3D interpolation? I'm not sure. There is one very obvious application of this 3D comparison, which is typically when you want to have generative models for point clouds. And this goes a bit with the slide I'm showing here. Imagine you have a generative model that spits out point clouds. Of course, you will need to, at some point, compare the point clouds that you generate with real data. And in that case, it's very common to use the Wasserstein distance as a loss between the two 3D shapes. So we need to pick up steam. So when can we compute optimal transfer, or when is it relevant to compute optimal transfer? Well, so far I've basically focused on those two examples, which is discrete to discrete, continuous to continuous. And there is a third one, which is actually very relevant for data applications, in the sense of statistics, where typically you have a parameterized density that you want to fit to a discrete measure. Optimal transfer suffers from the curse of dimensionality. What kind of realization should we consider? Will entropic realization work? Yes, it does work in some sense to mitigate this. I will mention it a bit later. So what is nice about optimal transport and the Wasserstein distance, etc., is that it doesn't really care about what your measure looks like if you use the Kantorovich formulation. You remember this inf of P belonging to the product of marginals? This actually always works. It doesn't really care whether the measure is continuous or discrete. So any of those three problems is actually, in theory, you can instantiate it. Computing it, solving it is a completely different story. And so the upper left, as I said earlier in the introduction, was solved by Danzig in his work when he introduced network flows and linear programs. Basically, the problem of finding the soldiers' routing was solved in 49. We have increasingly efficient solvers now, but this was more or less solved. The discrete to continuous problem is a lot harder. Interestingly, it has some nice applications in physics. One of them is designing reflectors, for instance, for cars, that reflect light in a nice way when you're driving. But it's usually described as a reduction to the discrete to discrete problem. The continuous to continuous problem, of course, is even harder. And all of those attempts at solving it basically either go through the PDE route. So there is this Benamou-Brognier framework in 98, but which only works in very low dimensional settings, or using some form of stochastic optimization. Recently, I didn't have this in this slide, but there is the nice, when you start basically by approximating a few things, there are many innovations that have been proposed recently using deep learning, and one of them was this idea of using, in the Wasserstein 2 case, this input convectional networks, which fall in this case. But let me just for now, because very often this is the source a bit of inspiration for all of those techniques, except for this Wasserstein 2 Brognier example. Let me just focus on the discrete to discrete problem. Oh, no, sorry. Let me just discrete on easy cases. So the first case I would like to go very quickly over with, but you should be aware of, is that when distributions are univariate, when they're basically on the real line, and the cost has some nice properties. More particularly, it has to be submodular in general, but then let's just say it's a function of the differences. It's translation invariant, and it is a convex function of the gap between x and y. Then in that case, essentially, optimal transfer is just about the quantile functions of the distributions. Optimal transfer basically tells you, forget about the densities, look at the densities from the point of view of their quantile distributions, and everything will be easy, and everything will be optimal transport-ish. And not only that, if you look at the quantile functions, you can compute the optimal transport cost in closed form. How do we get this? Well, it's essentially going to be the following. It's going to say, compute the quantile function of the two measures, and now just simply compute their gap by integrating the difference between those two quantile functions with the cost function C. So let me just show this visually, maybe it's easier. This is the two distributions, two densities. The first step towards the quantile function is to compute the CDF. This is the first CDF. This is the second CDF. Okay, so this CDF of mu, CDF of mu. Now compute the inverse CDF. So you just rotate, sorry, take the symmetric with respect to y equals x-axis. You just draw the y equals x-axis and take the symmetric, and this gives you the inverse. And this gives you now the quantile function. Once you have done that, computing optimal transfer distance between the two discrete measures, between those two, sorry, univariate measure, is as easy as integrating their gap and maybe applying this C function if you are doing something a bit complicated. Of course, if you just take that the cost is just simply the difference, as in the example from Monge, then it's just going to be integrating the difference between the two quantile functions. So this makes life very easy when you're dealing with univariate measures. Optimal transfer is a bit pedantic in this case, because the only thing it does is basically tell you switch from densities to quantile functions, and that makes a lot of sense in my opinion. The other particular case, I will go a bit fast here because it has a lot of nice applications, but I'm running a bit late, is when you're comparing two Gaussian distributions. One Gaussian defined by mu and sigma mu, another Gaussian mu sigma nu. Well, in that case, if you're using this particular cost again, the squared Euclidean distance, then the optimal transport distance between the two Gaussians has a closed form. And it's actually a very intuitive distance. It's something that says, well, whatever if you have two Gaussians, the distance between them is going to be the distance between their means, just the squared Euclidean distance between the means, plus a distance between their covariance, basically the ellipses that define those two Gaussians. And this is called the Burrs metric. That B here is a formula which is basically given to you here. The squared Burrs metric between the two distances, the two covariance matrices, is this formula. There's a lot of very nice things about this formula. I mean, if you like Gaussians, and who doesn't, you find nice things. So one of the nice things that you find out is that actually there is an optimal Monge map that takes you from one Gaussian to another, and those Monge maps are linear. So if you remember your probability 101 course, you know that if you take a random variable that has a Gaussian distribution, if you take a linear or even an affine transform of that random variable, you still get a Gaussian with a slightly different covariance matrix and a different mean. Well, it turns out that moving Gaussians like this using affine transforms guarantees optimality. So if you have two Gaussians, there's no better way, of displacing the masses than following a linear and affine map. And the affine map is the following. It basically does the following. It just says, when you take an x, add to x the mean of the second measure, and then subtract the mean, center your x with respect to the initial measure, and use a linear map, which is called this A matrix. And this A matrix is just this type of squared root where the two covariance matrices are intertwined. So it's actually quite easy to prove that this is an optimal transform map. So what I'm essentially saying is that if you go from here to here optimally, you're always going to follow this this affine map. And it's actually quite easy to prove this, and you can prove it using Brognier theorem. This is one of the nicest applications of Brognier theorem, but I'm going to go a bit faster because otherwise I will be short. There is another very simple case where you can compute optimal transfer in closed form, is when you're comparing two Diracs. And I think this makes the case, explains a bit why optimal transfer is nice. Somewhat when you have 2 points on the space, let's say x and y, you can compute their distance. Now, imagine that you're looking at those 2 points no longer as points, but as Dirac masses on those points. So you've kind of lifted, you've promoted those points as Dirac masses in the space of measures. Then what is nice about the optimal transport distance is that you still get that the distance, the Wasserstein distance between the two measures is actually the distance between the 2 points. So lifting the points towards measures and recovering the same thing shows you that somewhat Wasserstein is a bit of a canonical way to lift a distance on the base space towards the distance between probability measures. Now, and this goes a bit back to my initial example, the genomics. If you have two measures which have the same number of points. So here I'm putting the 1/n to ensure this is a probability distribution. And you have the same, you have two uniform measures of the same size. Then trying to find a coupling that is going to map mu to nu, okay, is going to be like solving for a square matrix of size n and n. And what you will find out is that finding the optimal matrix will guarantee, and this is called the Birkhoff theorem, that you will basically follow the solution that will look like this. It's going to be a permutation matrix in disguise. And this is why the linear assignment problem or the matching problem that I've told you about before is basically a subset of all the Wasserstein or optimal transfer problems. And why is it a subset? Well, it's a subset because here we are only considering, this is a way of parameterizing the set of permutations, which is the same thing as parameterizing a set of permutation matrices. And permutation matrices in this case are a particular kind of coupling with uniform marginals. So this is one particular example. The more general instantiation of the optimal transport problem, and again, I hope here you can see the analogy with respect to the barracks and the front lines in the counter-ridge problem, is basically you have a distribution on the left-hand side with different locations and different weights, and you want to find an optimal way of mapping this towards that. So this would basically involve knowing whether you're sending mass from each of those input locations to the target location. Now, let's write down this problem. So we have mu and nu, red, blue. Red is defined by weights and points. Blue, weights and points. There is a different number, maybe, of input and outputs, target points. We don't really care. And we are going to take that information and encapsulate it again a bit like in the Cuturi problem, remember the barracks, in two things which are going to matter. On the one hand, the marginal distributions, on the other hand, the cost matrix. So the cost matrix is typically going to be this thing, right? It's going to be a distance of xi, yj to power p. And the set of matrices, remember this was the matrices with row sums that satisfy the first marginal, column sums that satisfy the second marginal. And the problem will be about finding the matrix here, which satisfies those marginal constraints, that has the smallest dot product with respect to this rectangular cost matrix. So this is the optimal transport problem, the canonical optimal transport problem, which is very often one of the first examples studied in textbooks on optimization. Is it possible to derive closed deformed Wasserstein distance for any two mixture of Gaussians? No. It's not possible to get it in closed form in general. However, there are known upper bounds which are quite useful. And those upper bounds are basically the same thing as, I'm going to state it very quickly. You basically imagine that your mixtures of Gaussians are point clouds in the space of Gaussians. Okay, so you are lifting, and now a mixture of Gaussians is basically a bunch of different Gaussians in the space of Gaussians with different weights. And to define the cost of moving from one Gaussian to another, you use the Wasserstein distance that I defined earlier, that uses the covariance matrices. And now you solve the optimal transport problem in that space of Gaussians. This is an upper bound on actually trying to really do the hard work of displacing Gaussians optimally. So in the examples that I showed you earlier, where there were actually mixtures of Gaussian in 2D, I was not using that upper bound. I was really, discretizing the grid of R2 and then really doing the optimal transport. But in higher dimensions, you cannot discretize, and therefore there's no easy way of actually instantiating your problem. And so people usually resolve to this upper bound that I just described. So let me go back to the linear program. Linear program is this. And remember, I told you, whenever you have a linear program, continuous or discrete, there is always a dual. So let's try to write the dual very briefly. If you remember the dual is basically saying I'm maximizing a function of the first measure, integral of the function of the first measure, the integral of the function of the second measure, and then the first function at x plus the second function at y must be smaller than the cost of xy. Well, in a discrete world, it would be a lot simpler. It would just be integrate, take the dot product between alpha and a. So this is the measure, beta and b. So instead of having two functions here, I have a vector of size n and a vector of size m. And then we have a constraint, which is that alpha I plus beta j is smaller than the distance between xi, yj. So in that sense, we haven't really changed, the constraint. So it's pretty much what I told you in the continuous world. And it turns out that these two things, again, of course, in the discrete and the continuous setting are the same. It's actually quite interesting to interpret the dual. So let me take 1 minute to explain this. Suppose I get, on the one hand, I compute my P star. And the other hand, I compute my alpha and beta star. So independently, I solve those two problems. I know somewhat, that they should match in terms of the objective value. So why did I put here P star on the left? Well, because here I'm actually plotting, if I have 2 point clouds, red and blue, the optimal transport. If indeed, this is a barrack, and the size of the barrack is basically proportional to the size of the square, and this is the front line and it's proportional, etc. Well, this is the optimal transport. This means that those soldiers will go here, those soldiers will all go here, etc. So here I have solved, if you want, the very intuitive form of the primal problem, which is tell me who goes where. Let's think about the dual problem. What is the dual problem telling me in the continuous or in the discrete setting? It's giving me a value for each of the points in the input source, in the input problem, which is alpha. So we would have alpha 1, alpha 2, alpha n, and the value beta 1, beta 2, beta m in the output. And so I'm plotting here those two values. So here you could see immediately that this is going to be the values for beta. And here I'm plotting them using a color coding. And this is the color map that this refers to in both cases. And what essentially, remember, there's one very important constraint I have here, which is that alpha I, so if I, for instance, look at this value here, plus, let's take this one, plus this value here, so minus 40-ish, plus, let's say this is probably 37. This should be smaller than the distance between those two things, okay? What is interesting, if we take a step back, is that if you look at this, it seems that the relatively, to this, if you look at the dual variable here in this case, and the dual variable here in this case, well, it seems that the higher dual variables seem to be for this one, for instance, for the red. And if you look at the dual variable for the blue, it typically is in those areas. So in short, I want to give you just the intuition that what the dual problem is going to give you as an indication is, if you look at the blue targets and the red sources, what is really causing you the most pain? What is really being very costly when you're trying to do the optimal transport between those two distributions? And the higher the dual variable, essentially, the higher this point is actually like a friction point, if you want, something that is actually raising the Wasserstein distance. And it's pretty obvious. Imagine you are, for instance, those are distributions of bakeries, and this is the distribution of restaurants. This is the distance, okay? You computed it by just integrating the sum of those lengths. If you had a given chance of a second chance of moving around the bakery so that you have to pay less in terms of transportation, well, probably this is the one that I would probably try to move. And if you had the chance to move the restaurants, you probably move them in this direction. And this is precisely what is given to you in the dual formulation. So in other words, the primal problem gives you the way to move things around. The dual variables gives you the sensitivity analysis. It tells you basically how you could change your data to reduce the value of your objective. This is just a parenthesis. Let me just go back to linear programming. Again, remember those are the matrices P that belong to this. Those are matrices which are rectangular, size n times m. There's many of them that have the right marginals. This itself is a cost matrix. It has size n times m. So this is a space of matrices of size n times m. And within all those matrices, this very small set, this polytope, as we call it, of matrices that have the right marginals. The optimal transport problem is basically find the matrix in this set that has the smallest dot product with respect to mxy. And so obviously, if you just look at this, the one that has the smallest dot product is basically the one that is furthest to the left in the opposite direction of mxy. So this is a set of matrices that have the same cost, which goes they are orthogonal to mxy, and the one that is the best is here. And so the question is, how can you get there? How difficult is it to solve this linear program? I told you there are algorithms to do this. How easy is it? So this is a bit of a debated issue. What is the optimal complexity of solving the optimal transport problem? You will have a few TCS papers that propose bounds that might be a bit lower than what is given here. But most of them, I mean, at least to my knowledge, don't yield actual algorithms that people use. What people use as an algorithm typically is either something called the auction algorithm or the network simplex algorithm. And those algorithms are essentially cubic in the size of the problem. So as an LP, as a linear program, it's not so big in the sense that here, remember, the size of the problem is itself nm. So it's a quadratic size in terms of variables with respect to the problem that the measures. And so going from quadratic to cubic is not that much. In terms of data processing, of course, this is far too much. So this is a bit of a problem. If you use the linear program paradigm to solve this, you will get into trouble. The other reason, in my opinion, you will get in trouble, and this is a bit more fundamental from my perspective, computations is a problem, but there is another problem, which is instability, or if you want, differentiability of the solution. And so here is the reason I would never try to compute a matching, an optimal matching or an optimal transport plan that I want to use in deep learning using a linear programming solver. The reason is that if I perturb a little bit, you know, the x here, suppose I start moving it a little bit, and so I wiggle a little bit mxy. As you saw visually, for a long time, this p star is not going to change. So no matter what is the small, you know, variation I make in my data or the parameters of my neural network, this is not going to impact at all p star. So if p star is an important component that I want to use down the line in the deep learning end-to-end pipeline, essentially there's no gradient. There's a vanishing gradient problem there. If you look at this from a more mathy perspective, essentially the Wasserstein distance is a continuous function of the input, but it's not differentiable. And it's not differentiable because either it has zero derivative for a while, so p star doesn't change, or all of a sudden it's going to jump from one corner to the other, and this makes it not differentiable. So, and the third, maybe another argument that you might want, I mean, you may not be happy with, is that typically the way you solve network flows solvers is quite involved, quite complicated, and typically something that you cannot run on GPUs. So this kind of closes a bit my parenthesis. Optimal transport, essentially, you should really stick to the rules, you know, the definitions that I gave you earlier. There's a few cases where it has a closed form, univariate distributions, Gaussian distributions, more generally something called elliptic distributions. But when you start instantiating it on discrete data, you need to solve a linear program, and linear programs are costly. The end result is not differentiable, and it's not easy to parallelize on GPUs. So what is my opinion on linear time approximation algorithms? Well, you will see that this is using the synchron machinery that I'm going to introduce next. So stay connected for a few seconds. I will introduce the work on which this paper builds upon. So up to now, I told you something which, if you were to stop here, the presentation should not be the cause, for excitement about optimal transport, because essentially I told you, well, optimal transport is nice in theory, it does really great things, but when you have to compute it for samples, it's horrible. And not only did I tell you that it is horrible because it's slow, but I haven't even told you the rest, which is that it's also very unstable. And so let me just give you a quick explanation. Imagine you have data which comes to you in the form of samples. Those samples come typically from a distribution that is underlying. This is the basic assumption of statistical learning. And so what typically we do is we sample, we compute quantities, and then we look at what they look like. So there's two aspects to this. One is computational. How hard is it to compute, the Wasserstein distance between two samples? I've already introduced this. This is quite hard. And the other one is more statistical. And this was related to one of the questions in the chat. And by statistical, I mean basically, imagine I had access, if I had access to the entire densities, to the true Wasserstein distance between them. Could I ever hope to approximate that quantity with samples, with only my n and m points that I've been given? If this is not the case, it basically means that while I'm working on this, using this, I am thinking that I'm actually working on the true the difference between the true Wasserstein distance between the densities. But if this is completely different from this, then it's a bit, as being completely driving while being a bit blind. It's driving, trying to get to some objective, saying I want to minimize the Wasserstein distance between this and that, but because I'm always using only finite samples, and if this is far from this, then it's a bit like driving towards a direction that is not exactly the one that I want. And so this is not only bad from a computation perspective, but going through the linear programming way to solve the optimal transport problem. So people call this using the plug-in estimator. So by this, I mean taking the linear program that has been instantiated by Cuturi on densities and taking it as it is on samples, is known to be extremely unstable, in the sense that it has very poor sample complexity. And someone was saying the curse of dimensionality, and it's true. It basically says that if you want to approximate the Wasserstein distance between two distributions in RD with a squared Euclidean distance, for instance, then you will need to have a good quality of approximation, epsilon, let's say, a number of samples that is exponential in that quality of approximation. So if you are in dimension 2 or 3, you're fine. In dimension 1, actually, it's the square root of n. But if you're in dimension, let's say 10, everything is going to scale as 1 over n to the power 1 over 10. So this is a complete disaster, and clearly something that doesn't work. So there's lots of results on this. So if I have to say, if you stop the presentation now, is it useful to use optimal transport? You should probably say no, because computationally it's bad, and statistically it's bad as well, because of this curse of dimensionality. So my message is optimal transport is great as long as you remember why you're using it, and you're using it to actually play with data. Data is noisy, data is, you only have finite samples, etc. And so in that case, we know, just like with any other machine learning algorithms, that we need to inject some notion of regularity for this to make sense. Otherwise, we're faced with curse of dimensionality problems. And so it's very common, for optimal transport papers in machine learning to start with a nice story about Kantorovich, and then propose hacks along the way to compute optimal transport and feel somewhat a bit embarrassed by those hacks. But the point I would like to make in these slides is that in those hacks lie the real added value of the machine learning community to the field of optimal transport. We know that we can't use, the original tools. We have to develop new tools. And so there's been a lot of work, and I don't really have the time to actually provide you a full survey of all of the regularization approaches that people have considered. But one of them is, of course, try to look at the optimization problems and add assumptions whenever you want or whenever you can, or whenever you find it useful. So if you look at the dual problem, remember this is the dual, we're integrating over this. Well, you can start saying, okay, maybe instead of just computing this for any type of phi and psi functions, let's just say those belong to a specific RKHS of smooth functions. So we're going to limit things a bit, and then maybe start adding different ways of computing and regularizing those constraints. And so there's so the idea of using RKHS was introduced in a paper a couple of years ago, and more recently there's a nice, very interesting paper by a team, including one of my former students, who has been using sum of squares, basically a nice result of sum of squares and kernels to solve the optimal regularized formation of the optimal transport problem that has nice properties. You can also start, again, to look at particular cases that are relevant. So for instance, if you look at W1, I told you that this is the same thing as using test functions for phi Lipschitz test functions. And then you can think about, okay, I can probably try to come up with a family of functions which is Lipschitz. If you use neural networks, if you use ReLU activations and bounded coefficients, then you get Lipschitz functions by design. So let's just try to solve this directly as if it was a neural network problem. And this is the approach taken by the Wasserstein paper. You have to keep in mind, though, that you're not trying to solve anymore the Wasserstein problem, but it's more like a proxy that is regularizing in a certain way. I didn't include it in the slides, but there's another way to do this now, which was proposed last year with Wasserstein 2 using input convex neural networks. So instead of having a soup over phi, which is one Lipschitz, you would have a soup over an f function, which is convex parameterized by a neural network with an f star Legendre transform. The other way to do this is, instead of looking at the dual, look at the primal. And again, you can start regularizing in many possible ways. One way is, for instance, to simplify the cost function. You're going to maybe threshold it or use a specific type of distance that is going to make your life a bit easier. This is related to the one Wasserstein distance. You can start playing with the measures themselves, simplify them. So there was a question about mixtures of Gaussians. So for instance, you could, say, okay, you gave me data, I'm going to estimate a mixture of Gaussian on that data, and then I'm going to try to solve the problem with mixtures of Gaussians. You could project your data on subspaces. This is I will describe this in a few slides. And then there's another way, which is you can start imposing some constraints or regularizers on the coupling itself. And one of them is entropic regularization. There's been other regularizers that have been considered in the literature. So one first way, and again, I'm going to build on the result that I gave you on univariate distributions, is remember, optimal transform is more or less solved in 1D. You just need to take whatever distribution you have of data and compute the quantile function. This is as easy as sorting values if you're dealing with discrete samples. Again, this was the idea. This is very easy. So what you can actually do, and this was proposed in 2011, and has been the source of quite a few papers, is consider what people call this sliced Wasserstein distance. So if transport on the real line is easy, then it's why not just simply project your data on many different real lines that you're going to sample on the sphere, let's say, and compute the distance, sum of the distances on the sphere. So this is actually nice because it somewhat solves a bit constructively in a naive way the curse of dimensionality curse. But I should warn here that this is actually, although the name is sliced Wasserstein distance, this is nothing to do with the Wasserstein distance. This is actually a Hilbert distance between measures. It's a lot simpler than the Wasserstein distance, but it kind of has some interesting practical properties, but there's not much you can say more about it. The one approach that I would like to focus on today is entropic regularization. So the motivation behind entropic regularization is going to be geometrical. And it's going to be the following. You remember that I told you that the optimal transport problem basically is solved, by looking at those vertices of the transportation polytope and working very hard, sweating to get to the vertex that is optimal. This is a philosophical point, linear programming is all about finding vertices. Convex optimization, on the other hand, is more often about finding something that is in the interior of your set. And there's a long tradition of, either trying to find points in the vertices by slowly going through the interior. This is called the interior point methods. But here I'm going to actually take a more aggressive stance, and I'm going to say, in practice, I will prefer to stay somewhere inside here, because this is going to vary more continuously with respect to the parameters. So when you regularize, when you forget about jumping from one vertex to the other, you're going to stay somewhere in a smooth curve, inside your polytope. And this is not going only to be easier to compute and faster to compute, but my point is also that it's going to be differentiable. So the approach is actually very easy, in the sense that this was proposed by economists again in the 60s. And the idea is to simply take the linear program, remember that we have. This is linear constraint, this is linear objective, and add a strongly convex regularizer. And the strongly convex regularizer is going to make this a bit curved. It's going to be, in this case, the entropy. And this was considered in the 60s by people in the economy, because they were saying, when we actually compute optimal transport, we realized that the p stars, that we compute, which could predict some transportation patterns, are too sparse. They are not diffuse enough. Reality, when we look at transportation patterns of people, etc., reality seems to be somewhat doing an optimal transport, but not as sparse and spiked as what is predicted by those models. So we want to add some kind of blur. And to add blur, what we're going to ask is, we are going to minimize transportation plans that have a low objective, low cost, but at the same time need to have slightly high entropy. Okay, minus entropy, because you're minimizing. This means that you want some entropy. And so let me try to show you visually a bit what this means. Imagine you're solving the optimal transport problem. Again, I told you this has a closed form, but let's say we're doing it. We're solving it using a linear program between this distribution and this distribution. In that case, I have discretized the two distributions here and here. So you could almost basically imagine that this is a histogram, and I'm basically trying to transport this to this. This is going to be a square matrix. If you actually run the linear program, you will find out that your solution is extremely sparse, meaning that most of those areas are going to be zeros. And actually, this is not a surprise. This is actually a known result of linear programming. It's very clear that when you solve linear programs, the solutions that you get are always sparse. Here, by adding this, I'm essentially going the opposite direction. I don't want something that is sparse, because something that is sparse is very low entropy. And since I'm asking for a bit of entropy, because gamma here is positive, I will start observing, if I plot the solutions, things that look a bit like this. They look like the initial problem, but they are increasingly blurry. And when gamma goes to infinity, what I'm asking is a coupling that has to be maximally entropic. And I know which one it is. It's just the product of the two marginals. So to summarize, by throwing this thing here and playing with this gamma, I am interpolating on the one hand between the optimal transport, the one where a few things move around, and the maximally entropic thing, which is the soldiers moving all around without really knowing what they were doing. They were just moving proportionally, which is this kind of completely dumb, very naive approach to transportation. I don't even look at this, right? If gamma is infinite, I don't even look at the cost. I only look at whatever is entropic, and I know the solution. It's just the product. And the reason this regularization is nice, there's many of them, but one of them is that the algorithm that you get to compute this solution is very, very simple. It is a very, let's say, basic type of algorithm. And I would like to walk you through very quickly through this. Essentially, you're saying this is the minimum of a strongly convex function. So this is convex optimization land. We know very well how this works. This is constrained, 2 linear constraints, no inequality constraints, so that's even easier. We don't need to handle inequalities. We can just handle equalities. And so here in this case, if you just write first order conditions of the Lagrange, if you just use the method of Lagrange multipliers, you know what the solution will look like. And the solution, if you just write down, this is the Lagrangian. Here I've added the objective. This is the linear term minus the entropy, which is plus plus. And here I'm adding a Lagrange multiplier alpha and beta for each of the equality constraints. Then if you just work it out, if you just say that the gradient of this and the solution, the optimal solution is going to be 0, you find out that the solution has this magical factorization, which is, it has to be equal to a term ui, a term vj, and something in the middle kij. And this kij, it's given to me. I don't need to compute it. It's basically the exponential of minus the cost matrix divided by gamma. And let me just be a bit brief here. If I know that the shape of the solution is this factorization, the way to actually find out what it could look like is to re-inject the constraints. And you remember the constraints where P gamma has this shape, but also P gamma is such that P gamma times 1 is equal to A, and P gamma transpose times 1 is equal to B, right? So this is the 2 constraints that I want my couplings to satisfy. And so if I just re-inject this in here, I get those 2 equations with respect to U and V. And those 2 equations with respect to U and V, I can massage them a bit. It's just simple linear algebra. And it basically boils down to saying, well, the solution that I'm looking for, the solution to this problem, is going to be defined as this factorization, and U and V must satisfy those 2 equations. So those 2 equations are not so obvious to solve because they are non-linear. You can see that there are some divisions involved there. But there is one, what are possible alternatives to entropic regularization? You could use L2 regularization, for instance. Recently, we've introduced some low rank regularization of the coupling. There are a few of them, but to my knowledge, entropic is better behaved numerically and faster, more scalable in a wide range of settings. And people have studied it a bit more in depth, typically the statistical aspects of the entropic regularization. So I would say it's not obvious entropic is really the way to go. I mean, it's the only way to go, but for now it is the way to go in the sense that this is where we know that it works quite well in practice. So if you just look at those 2 nonlinear equations, you need to find 2 vectors U and V that satisfy this. You might wonder how to find them. Well, you don't need to think too much. It's just a question of finding, this is a fixed point iteration, basically. This is a type of X is equal to F of X type of problem, and it works to do the fixed point iteration. So you would start with a U is equal to V, initialization for V0, let's say, and then you just alternate. U is equal to A divided by KV, V is equal to B divided by K transpose U, and then you do this over and over and over again, and then you get to a solution. Let me just turn on the light for a second. Sorry. So this is the synchron algorithm, and it actually is surprisingly simple to solve something that is surprisingly hard to solve for a linear program. So if you look at the PDF, I have tried to illustrate a bit how to, what it does look like. But you can really think of this as like a two-step algorithm. It's a while loop, and inside a repeat loop, and inside there are two simple instructions that you can carry. Let me just say that although this might appear a bit complicated or magical, if you like optimization, the Synchron algorithm is actually a very simple algorithm that has a very well-known understanding. And it's basically something called block coordinate ascent on the dual. So let me try to explain this. This is, you remember, regularized optimal transport. You remember that the primal, if you don't have this, we had a dual problem, right? Well, it turns out that if you still add entropy, of course, because this is a convex problem, you can very easily instantiate an equivalent dual problem. And the dual problem is this thing, which is actually very nice because contrary to the dual problem of the original formulation, this dual problem is unconstrained. And it's essentially doing the following. It's basically, here you should probably recognize what we had before. This is just the objective of the initial dual. Before, what we had was this constraint of alpha I plus beta j. Maybe you might remember this, Cij, something like that. Okay. Well, this, we no longer use it. And we're essentially using something that looks, if you look a bit more in detail, like a soft kind of constraint of this, a regularizer that tries to enforce this constraint. So if you look at this problem, even if you know nothing about optimal transport, this linear minus exponential of something, k exponential of something, there is a very simple approach to solve this problem. And it's actually to optimize first on alpha until you have canceled the gradient with respect to alpha of this energy, and then optimize with respect to beta. And if you do this over and over, this is exactly the same thing as doing Synchron. Let me try to show you why. Well, take this energy, compute the gradient of that energy with respect to alpha and with respect to beta. It's just simple calculus. The first gradient is this, the second gradient is this. So if I want to cancel this gradient with respect to alpha, this is the update that I need to make. I'm just setting this is equal to 0 and deriving alpha from this. And the same thing, if I set this is equal to 0, then I will get this update here. Okay. So this is a simple way of solving this optimization problem. Now imagine that I parameterize my U and V before as exponential of alpha divided by gamma, exponential of beta divided by gamma, then I get exactly the same updates. Basically, what I'm doing here is strictly equivalent to doing the first update in Synchron. What I'm doing here is strictly equivalent to second update in Synchron. So there are a few slides here where I'm trying to explain the relationship between Synchron, the Wasserstein time distance, and the energy distance, which you might have heard about. I encourage you to look at it, but I'm going to skip this because I'm really running short of time. And so there was a question, actually, now I remember, which was, I think, so optimal transport suffers from the curse of dimensionality. What kind of regularization should be considered? Will entropic regularization work? And yes, the answer is entropic regularization kind of works for the curse of dimensionality for optimal transport, in the sense that it can recover 1 square root of n sample complexity when you are computing the entropic, when you're really taking as a ground truth the entropic regularized problem. Let me just be brief. I want to conclude the course on this aspect, which to me is dear to me, which is differentiability. So I really want you to think about this matching problem as something that goes beyond just computing the matching, but having an idea of how can we understand how the matching changes when the input changes. And so let me try to illustrate this very simply in this slide. Imagine that I have solved my optimal transfer problem between A and B, the red and the blue. What I'm asking is, what will happen with the Wasserstein distance if I just perturb it a little bit? By this, what happens if I change a little bit the weights of the left-hand side? And the other question is, what happens with the Wasserstein distance? Can I compute the gradient of the Wasserstein distance with respect to changes in the locations? So this time I'm not going to change the weights. I'm just going to change a little bit the location. So if the only thing that I'm looking at is how does the Wasserstein distance vary, okay? If you really want to do just basic calculus on the Wasserstein distance, so the minimum, the objective, then if you know a bit about this, you know that this type of situation can be handled with the Danskin's theorem. In the sense that Danskin's theorem tells you something like this. It tells you if, for instance, you are computing f of x is equal to the minimum of some function g of x and z, where z belongs to some convex set, or actually something more general, then you can find that your gradient of f with respect to x, okay, is essentially going to be the Jacobian. I need to remember this one. The Jacobian with respect to z of x as z star times the gradient with respect to x star with respect to the gradient with respect to g of with respect to z I need to forget about this. So it basically says if you're changing a little bit, for instance, your x, this is going to be, yeah, okay, so this is the gradient with respect to x of g. Compute it at, so let me just, so if your f of x is equal to minimum of g of x, z, with respect to z belonging to some set, then the gradient of f at x is going to be the Jacobian of g no, sorry, it's not the Jacobian. Yes, sorry, no, what am I saying? Sorry. After 3 hours, I'm getting a bit confused. It's going to just simply be the gradient of g with respect to z at z star, basically. This is more simple than that. It is basically going to tell you, it's as if you are basically only changing sorry, it's the gradient with respect to, I'm sorry, it's a bit late. Yeah, this is much simpler than that. It's basically as if you were saying your f of x locally is going to look like g of x comma z star, where z star is the argmin of g of x z, okay, for that particular x. So it's as if basically nothing was really changing. The z star was not really changing. And so the only thing you need to change is how g varies with respect to x. So somewhat you're freezing, if you want, the optimization variable. So in this case, what this simply means is that when you're going to try to predict how the Wasserstein distance changes with respect to either the weights or the locations, you're just going to shoot, I mean, just reuse the optimization variables that you recovered in the first place. So this means that if you want to know how this changes with respect to the weights A, I'm just going to compute alpha star and beta star and pretend this is what the Wasserstein looks like. It's going to look like alpha star transpose A plus beta star transpose B. And so locally, it's as if I will pretend alpha star and beta star don't really change with respect to A and B. And so everything goes well. So this is the Danskin theorem for variations in the weights. If you're taking variations in locations, assuming the distance is square Euclidean distance to simplify the analysis, then essentially everything is going to behave like a quadratic function of the weights. of the location, sorry, which is going to be freezed. It's as if we were saying, you know, the mean of PC of xy is going to be locally equal to P star CXY. And therefore, this is going to be a quadratic function in x and y. So somewhat you're saying Danskin tells you optimize first, freeze the optimization variables. And if you want to know basically how Wasserstein will change, just freeze the optimization variables and just do the small elementary computations, elementary calculus around those optimization variables. So this is great if what you want to do is just differentiate Wasserstein distance. So what I'm essentially saying is, if you're looking at the value of the dot product here of the optimal solution with respect to this, the cost, then if you just change a little bit, you know, the cost, the one parameter of your problem, then what we will be essentially looking at is what is the value of this new optimal transport distance, optimal transport plan computed with respect to this. And so in that case, this variation is actually a minor or negligible with respect to this variation. And so you can directly use Danskin theorem. So if really what you want to differentiate is Wasserstein, easy. If what you want to differentiate, on the other hand, is the argmin, and remember the argmin is going to be P star, then this is harder. So here by square, I mean anything. This could be, for instance, AX, some parameters, maybe the cost is parameterized, as we can very often see this in applications. So this is easy, this is harder. Jacobian of the P star is harder. And at this point, there's basically two different ways to look at this. So I think I will take maybe 6 minutes more and then close. The first way, remember, everything was done using, I mean, all of our computations were done using the Synchron algorithm. And the Synchron algorithm was this very simple routine that was updating two values iteratively, two vectors iteratively. And then at the end, you could spit out, you know, the solution as being the solution corresponding to the whatever you got after, let's say, big L iterations. If you want to differentiate this with respect to this, or this parameters, you can by just doing unrolling. Unrolling is simply the idea that we're going to hijack the very nice automatic differentiation machinery of deep learning to just simply instantiate a computational graph that went from the inputs to the output, which was this PL. And we are going to use, you know, PyTorch, JAX, TensorFlow to simply compute automatically by backpropagation of those iterations, the differential. The other approach, and so this was highlighted for the first time, to my knowledge, in a very nice paper by Adams and Zeman in 2011, and was used again many times after that. The other nice approach to consider this Jacobian of how the matching will vary with respect to the input is, I would say, a mathematician view by opposition to a programmer view. And what a mathematician does is the following. The mathematician says, there is a mapping that takes my measures and my cost and my regularization and everything and computes a pair of optimal dual variables. And what is nice about those optimal dual variables is that they are, sorry, this is not zero. They satisfy, they are the roots of an equation, which is the following. This equation basically tells you that the dual variables are optimal. So at the optimum, my inputs and the two variables that I get out of my Synchron algorithm satisfy a root equation. So now, if I want to know how this varies with respect to any of these things here, there is a very nice way to do this mathematically, and it's to use something called the implicit function theorem. The implicit function theorem tells me basically the Jacobian of the output, so f of this map, with respect to anything that I'm considering here, can be computed by taking the Jacobian of this root equation with respect to the output, basically those two things, inverting it and computing it at the optimal solution that was speeded up by f, inverting it and computing the Jacobian of, again, this root equation here with respect this time to whatever I want to differentiate against. So this is, if this is the first time you're seeing this, is a bit scary. According, you could say this is a bit scary, but this is actually very well understood. And the other thing that I would like to say is that in when you're doing, if you're a bit familiar with JAX and PyTorch, what you know is that the important thing in automatic differentiation is not applying Jacobians, but is the application of the transpose of a Jacobian, what people call a VGP, vector Jacobian product. And so this is just simply transposing this expression. And so this is scary, but fortunately, a bit like deep learning, where nobody actually programs his or her own, backpropagation, we are now able to do this automatically. And this is one of the goals of this optimal transport toolbox that I just described. So all of those Jacobians here, those blocks, can actually be computed automatically with JAX. The linear solver is going to be also called by JAX. And not only that, but you can even differentiate through this linear solver. And so all of those big steps that make this a bit complicated are actually implemented in our toolbox. So if you're interested in this, you can take a look at some of the notebooks that we wrote and see, for instance, that it's very easy to compute automatically the Hessian, for instance, of the optimal transport potentials, or for instance, the Wasserstein distance automatically, thanks to those approaches. So to conclude, optimal matchings are used everywhere in machine learning. So either you can use them to compute a distance, but I think we're beyond a bit that. What we want to do is more like use the matching itself. We need to regularize to scale up, to make them more robust. So this is more a statistical perspective. But most importantly, in my opinion, to make sure there is some gradient. That you can, this P star is not staying there in this corner forever if you change a little bit the variables. And to differentiate through this, there's two ways. One is unrolling, which is like a all size fits all solution. And the other one is implicit differentiation, which is a bit more complicated to implement, but usually more efficient. And let me just really very quickly conclude with a few research topics. If you're interested in this, you could look at the slides. A few interesting, exciting research topics is speeding up the synchron fixed point iterations, generalizing synchron to continuous spaces. So instead of having a synchron algorithm for vectors, having one for functions. So again, interesting stuff happening there. Other regularizers are actually being investigated. Let me just say that there are other unbalanced formulations of optimal transport. I didn't mention, I always assume that the coupling had the right marginals, but you can introduce some penalizations, and they work very well with synchron as well. Brenier-Monge topics is the idea of this nascent field of using neural networks that are convex to kind of be able to use directly some results like Brenier to solve optimal transport problems. And I haven't mentioned this proximal optimization in the space of measures, which is the JKO paper, which is super cool, one of the most exciting results in optimal transport. But I hope if you follow this course, you might be inspired to start looking into this. Thank you.
Thank you very much. Thank you. Thanks, Dr. Marco Cuturi. And I know we are running out of time, but because it's unusual, you can be here with us. So probably we let the student grab the last chance, they can type their question. And we are waiting for the student type the question. Please allow me to ask a general question. We have a general question to the speaker. So after I add this question and after the speaker answer this question, then we do not accept new question. Okay, you can type your question quickly. Okay, so my general question is, you have joined the MLSS so many times, and you have organized machine learning summer school, even yourself. So do you have any suggestion to the audience, to the students to participate in machine learning summer school, to learning machine learning? Thank you very much. This is the general question.
So the suggestions I would have, I mean, my experience, of course, is more based on like the in-person interactions of the MLSS. So it's a bit of a sad answer to say that This is I think a crucial part of the summer schools. So I would almost encourage all of you to reapply in the future for another MLSS to experience this. What I would say is that don't be too hard on yourselves. Out of experience, it's common to feel a bit disoriented by so much material, and it's very hard to digest it in 2 weeks. So don't be too hard on yourselves. If you feel that, for instance, you haven't understood some parts of this lecture or other lectures, this is completely normal. The idea here is to give you a sample. It's as if you were going to a big restaurant with dozens of tables. You don't have to eat everything and be able to swallow everything. It's fine if you just sample a little bit, and then maybe a few years from now, you go back and think, now I understand maybe why this was mentioned in that summer school. So this would be my main advice. Don't be too puzzled by so much content.
Thank you very much. This is a very useful suggestion to the students. So we have new question in the chat room.
Yes. So another question, I saw your paper about Gaussian OT. So I guess you're mentioning the relaxation of, the regularized Wasserstein distance or single divergence between Gaussians. It may be related to some way. It's also related to dimensionality. So I'm not sure I understand the question itself, but let me maybe sketch one answer. So in the paper you mentioned, I understand you're talking about the idea that I told you earlier that there was a closed form for optimal transport, the linear programming formulation, and that closed form was for univariate distributions and Gaussian distributions. For the entropic case, when we were regularizing for entropy, for a long time we didn't know about a closed form solution for Gaussians. So meaning if you wanted to instantiate the counter-H problem with this regularization, is it possible to have a closed form solution? And it turns out that a few people in the last years have came up with an answer to this. And in this NUIPS paper last year, we kind of synthesized this answer and added new results that also apply with the balance case, etc. And so in a sense, your question is, does it beat the curse of dimensionality? I would say that it kind of follows the pattern that I described earlier, which is one way to regularize is indeed to simplify the measures. And so basically turn them into a Gaussian and then use a closed form. Here we were introducing another closed form. And yes, I think it is helpful. So for instance, people use, for GANs, people have been using a lot of Frechet inception distance. Maybe you're familiar with it. So this Frechet inception distance is basically trying to look at the two distributions of generated images and just using second order moments compute a notion of distance between them. And they use this as a score to score whether generative models is working appropriately. So they're using Gaussian distributions on some intermediate layer representation. And I think, yes, if people find this so useful, it probably reveals that somewhat this notion of Gaussian transport is quite robust to dimensionality. So yes.
Thank you very much. Because we are running out of the time, so we have to stop it here. So let's thank Dr. Marco Cuturi to give us an excellent overview of optimal transport today. Thank you very much. Thank you. Thanks the speaker.
I really want to thank the organizers again. Thank you very much for all this. And thank you to everyone who followed the lecture. Thank you a lot.